Welcome, and thank you for joining me on this gentle journey through one of the most fascinating mysteries in modern astronomy. Tonight, we are going to explore the remarkable story of dark galaxies, those enigmatic cosmic structures that challenge everything we thought we knew about how galaxies form, evolve, and exist in our universe. So settle in, find a comfortable position, and let your mind drift among the stars as we unravel this captivating tale together. When we think about galaxies, our minds naturally conjure images of magnificent spiral arms sweeping through space, brilliant cores blazing with the light of billions of stars, or perhaps the soft, diffuse glow of elliptical galaxies hanging like cosmic cotton in the void. These are the galaxies we see in astronomy books and planetarium shows, the photogenic celestial objects that have captured human imagination for over a century since Edwin Hubble first proved their existence beyond our own Milky Way. But what if I told you that some of the most important galaxies in the universe might be ones we can barely see at all? What if the cosmos is filled with enormous structures, some as large as our own Milky Way, that contain almost no stars? These are the dark galaxies, and their story is one of scientific detective work, technological innovation, and profound questions about the nature of matter itself. The concept of a dark galaxy might seem almost paradoxical at first. After all, we define galaxies primarily by their stars, those nuclear furnaces that convert hydrogen into heavier elements while releasing tremendous amounts of energy as light. A galaxy without stars, or with very few stars, seems almost like an ocean without water or a forest without trees. And yet, as we have come to understand over the past several decades, stars are not actually the most important component of most galaxies. They are merely the visible tip of an enormous invisible iceberg. To truly appreciate the story of dark galaxies, we need to first understand something fundamental about the universe we inhabit. The matter that makes up everything we can see, every star and planet, every nebula and asteroid, every grain of cosmic dust, represents only about 5% of the total matter and energy content of the cosmos. The remaining 95% consists of mysterious substances we call dark matter and dark energy, neither of which interacts with light in any way we can directly detect. Dark matter, in particular, plays a crucial role in our story. This invisible substance makes up roughly 27% of the universe, and it provides the gravitational scaffolding upon which all visible structures are built. Galaxies, including our own Milky Way, are embedded within vast halos of dark matter that extend far beyond their visible boundaries. Without dark matter, galaxies as we know them could not exist. The gravitational pull of visible matter alone is simply insufficient to hold these enormous structures together. Now, here is where things become truly interesting. If dark matter provides the gravitational framework for galaxies, and if stars are merely a secondary feature that forms within this framework under the right conditions, then it becomes possible, perhaps even inevitable, that some dark matter halos might exist without ever having formed significant numbers of stars. These would be dark galaxies in the truest sense, vast reservoirs of invisible matter occupying the same cosmic real estate as their luminous counterparts, but remaining hidden from our telescopes. The search for these elusive objects has been one of the great quests of modern astronomy. It has required us to develop entirely new ways of seeing the universe, to push our instruments to their absolute limits, and to think creatively about how we might detect something that by definition does not want to be seen. Along the way, we have discovered not just dark galaxies themselves, but an entire spectrum of low surface brightness objects that blur the line between visible and invisible, challenging our traditional categories and expanding our understanding of galactic diversity. As we journey through this story together, we will explore the theoretical predictions that first suggested dark galaxies should exist, the painstaking observational campaigns that eventually found them, and the ongoing research that continues to reveal new examples and new mysteries. We will meet individual dark galaxies with their own unique characteristics and histories. We will examine the cutting-edge technology that makes their detection possible, and we will consider what these ghostly objects tell us about the fundamental nature of the universe. But beyond the science, there is something deeply poetic about dark galaxies that I hope you will come to appreciate. In a cosmos that often seems dominated by brightness and spectacle, these quiet giants remind us that not everything of importance announces itself with fanfare. Sometimes the most significant things in the universe are those that remain hidden, patient, waiting for someone curious enough to look beyond the obvious. In that sense, dark galaxies are a metaphor for so much in life, a reminder that the visible surface of things rarely tells the complete story. So let your breathing slow and your thoughts settle as we begin our exploration. There is no rush tonight. The dark galaxies have been waiting for billions of years, and they will wait a little longer while we take our time to understand them properly. Let the gentle rhythm of this narrative carry you along, and if sleep finds you somewhere along the way, know that the universe will still be here, with all its mysteries intact whenever you choose to return. The night sky that our ancestors knew was limited to what the naked eye could perceive, perhaps a few thousand stars on the clearest, darkest nights. But the universe we have discovered through our telescopes is incomprehensibly larger and stranger than anything they could have imagined. Within the observable universe alone, there are estimated to be roughly 2 trillion galaxies, each containing anywhere from a few million to several trillion stars. The total number of stars in the observable universe is something like 700 sextillion, a number so large that it defies any meaningful comprehension. And yet even this staggering census of luminous matter represents only a small fraction of what is actually out there. For every galaxy we can see, there may be others lurking in the darkness, their presence betrayed only by the subtle gravitational influence they exert on their surroundings. For every bright spiral or elliptical galaxy that shows up in our surveys, there may be numerous dark counterparts that slip through our detection methods entirely. The universe we see is not the universe that is. This realization has profound implications for our understanding of cosmic history and structure. The distribution of matter in the universe, both visible and invisible, determines how gravity shapes the large-scale structure of the cosmos. Galaxies are not scattered randomly through space, but are organized into a vast cosmic web of filaments and walls surrounding enormous voids where almost nothing exists. Dark galaxies, if they are as numerous as some theories suggest, could represent a significant component of this cosmic architecture that we have been systematically overlooking. The story of how we came to recognize and study dark galaxies is therefore not just a tale of astronomical discovery, but a lesson in scientific humility. It reminds us that our picture of the universe is always incomplete, always subject to revision as new observations and new ideas challenge our assumptions. The cosmos has no obligation to conform to our expectations or to make itself easy to understand. It simply is what it is, and our job as curious beings is to keep asking questions and keep looking deeper, even when, especially when, what we find surprises us. To understand dark galaxies properly, we must first establish what we mean by the term and how these objects fit into the broader classification of galactic structures. This requires us to think carefully about what a galaxy actually is, a question that turns out to be more complicated than it might initially appear. In the most basic sense, a galaxy is a gravitationally bound system containing stars, stellar remnants, interstellar gas, dust, and dark matter. The key phrase here is gravitationally bound, meaning that the various components of the galaxy are held together by their mutual gravitational attraction rather than simply happening to be near each other in space. This distinguishes galaxies from temporary groupings of stars or from the larger scale structures like galaxy clusters, which contain multiple galaxies bound together. Traditionally, we have classified galaxies based on their visible appearance. The morphological scheme developed by Edwin Hubble in the 1920s and refined by subsequent astronomers. This system divides galaxies into spirals, ellipticals, and irregulars, with various subcategories based on features like the tightness of spiral arms or the elongation of elliptical shapes. But this classification scheme is inherently biased toward what we can see. It tells us about the distribution of stars and luminous gas, but says nothing about the underlying dark matter structure that actually dominates the mass of most galaxies. A dark galaxy, in the strictest definition, is a galaxy-sized dark matter halo that contains little or no stars. These objects have the gravitational mass of a typical galaxy, but lack the luminous component that would make them visible through conventional astronomical observations. They are, in essence, the skeletal framework of a galaxy without the flesh and blood of stellar populations. However, this strict definition represents only one end of a spectrum. In practice, astronomers have discovered a wide variety of objects that fall somewhere between completely dark and normally luminous. These include galaxies with extremely low surface brightness, meaning they contain stars but spread so thinly across such a large area that they are incredibly difficult to detect. They also include galaxies that are gas-rich but star-poor, containing vast reservoirs of hydrogen that have never condensed into stellar nurseries. The boundaries between these categories are fuzzy, and different researchers sometimes use the term dark galaxy in different ways. One useful way to think about this is in terms of the mass-to-light ratio, a measurement that compares the total mass of a galaxy, including dark matter, to the amount of light it produces. A typical spiral galaxy, like the Milky Way, has a mass-to-light ratio of around 20 to 30 in solar units, meaning that for every unit of light the galaxy produces, there are 20 to 30 units of mass present. Most of this mass is dark matter, but there is still enough luminous matter to make the galaxy readily visible. Dark galaxies, by contrast, can have mass-to-light ratios in the hundreds or even thousands. This means that an enormous amount of mass is present while producing only a tiny amount of light. Some dark galaxies may have mass-to-light ratios approaching infinity, containing essentially no stars at all, while still possessing the gravitational mass of a substantial galaxy. The existence of such objects was predicted by theoretical models long before any were actually discovered. In the standard model of cosmology, dark matter halos form first, condensing out of the primordial density fluctuations in the early universe. These halos then serve as gravitational wells into which ordinary matter, primarily hydrogen and helium gas, can fall. Under the right conditions, this gas cools, condenses, and eventually forms stars. But the key phrase is under the right conditions. Not all dark matter halos will necessarily accumulate enough gas or have that gas cool efficiently enough to trigger star formation. Several factors can prevent a dark matter halo from forming stars. If the halo is too small, it may not have enough gravitational pull to attract and retain significant amounts of gas, especially in the presence of energetic radiation from nearby sources that can heat the gas and prevent it from cooling. If the halo forms in a region of space that has already been swept clean of gas by previous generations of galaxies, there may simply be no raw material available for star formation. And even if gas is present, various feedback mechanisms can prevent it from collapsing into stars, including turbulence, magnetic fields, and heating from cosmic rays. The theoretical expectation, therefore, is that the universe should contain many more dark matter halos than visible galaxies. Simulations of cosmic structure formation consistently predict a large population of low-mass halos that should exist but that we do not see as luminous galaxies. This discrepancy, sometimes called the missing satellite problem, has been one of the enduring puzzles in cosmology. Dark galaxies represent one potential solution, the idea that these halos do exist but simply fail to form stars. But dark galaxies are not limited to small low-mass systems. Some of the most intriguing examples discovered in recent years are massive objects, comparable in size and dark matter content to the Milky Way, that nonetheless contain very few stars. These objects are particularly puzzling because they seem to have had all the ingredients necessary for prolific star formation, but somehow failed to do so. Understanding why requires us to think carefully about the complex physics of galaxy formation and the many ways in which this process can go wrong. One important concept here is that of the baryon fraction, which measures the proportion of a galaxy's mass that consists of ordinary matter, also called baryonic matter, as opposed to dark matter. In the universe as a whole, baryons make up about 16% of the total matter content, with dark matter comprising the remaining 84%. However, individual galaxies can have baryon fractions that differ significantly from this cosmic average. Bright, actively star-forming galaxies typically have baryon fractions close to or even exceeding the cosmic average, indicating that they have been efficient at accumulating ordinary matter within their dark matter halos. Dark galaxies, by contrast, tend to have much lower baryon fractions, sometimes only a few percent of the cosmic average. This suggests that something has either prevented them from acquiring baryonic matter in the first place, or has stripped away matter that was once present. The gas content of dark galaxies is particularly interesting. While these objects may lack stars, many of them contain substantial amounts of hydrogen gas, the raw material from which stars form. This gas can be detected through radio observations, specifically by looking for the characteristic emission of neutral hydrogen at a wavelength of 21 centimeters. The presence of gas in dark galaxies indicates that the problem is not a lack of raw material, but rather a failure of that material to collapse and ignite stellar fusion. Several mechanisms have been proposed to explain this failure. One possibility is that the gas in dark galaxies is too hot or too turbulent to collapse under its own gravity. Star formation requires gas to cool and condense into dense molecular clouds, and anything that heats the gas or stirs it up can prevent this process. Another possibility is that the dark matter halos of these galaxies have unusual properties, perhaps being more extended or less concentrated than typical halos, which would reduce the gravitational forces acting on the gas and make collapse less likely. Environmental factors also play a role. Galaxies do not exist in isolation, but are embedded in a cosmic web of matter and influenced by their neighbours. A dark matter halo that forms in a dense environment surrounded by other galaxies may have its gas stripped away by tidal forces or by the pressure of hot intergalactic gas. Alternatively, a halo that forms in an unusually empty region of space may simply never encounter enough gas to begin forming stars. The diversity of dark galaxies reflects the diversity of conditions in the universe. Some are ancient objects, relics of the early cosmos that formed their dark matter, halos billions of years ago, but never progressed to star formation. Others may be the remnants of once luminous galaxies that have been stripped of their stars and gas through interactions with larger neighbours. Still others may be in a transitional state, containing gas that may eventually form stars given enough time. Understanding this diversity is one of the major goals of current research into dark galaxies. By studying individual objects in detail and comparing their properties to theoretical models, astronomers hope to unravel the complex physics that determines whether a dark matter halo becomes a bright galaxy, a dark galaxy, or something in between. This research has implications not just for our understanding of galaxies, but for fundamental questions about the nature of dark matter itself. The properties of dark matter halos, including their density profiles, their shapes, and their clustering behavior, are predicted by different theoretical models to have specific characteristics. By studying the dark galaxies that these halos produce, we can test these predictions and potentially distinguish between competing theories of dark matter. In this sense, dark galaxies serve as cosmic laboratories, allowing us to probe the invisible majority of the universe through its gravitational effects on the small amount of visible matter present. As we continue our journey through the story of dark galaxies, keep in mind this fundamental duality. These objects are defined by absence, by what they lack compared to normal galaxies. But they are also defined by presence, by the enormous amounts of dark matter that give them structure, and by the gas that many of them contain. They are not simply empty voids in space, but complex physical systems with their own histories and dynamics. Understanding them requires us to look beyond the light and to develop new ways of seeing the invisible architecture of the cosmos. The history of dark galaxy discovery is a fascinating tale of technological innovation, theoretical prediction, and serendipitous observation. It spans several decades and involves astronomers working across the electromagnetic spectrum, from radio waves to visible light to X-rays. Each new detection method has revealed different aspects of these elusive objects, gradually building up our understanding of their nature and prevalence. The story begins, in some sense, with the broader recognition of dark matter itself. In the 1930s, the Swiss astronomer Fritz Zwicky was studying the Coma cluster, a rich collection of galaxies about 300 million light-years from Earth. By measuring the velocities of individual galaxies within the cluster, Zwicky calculated how much mass would be needed to gravitationally bind the cluster together. To his surprise, he found that the visible matter in the galaxies was far too little to account for the observed motions. The cluster seemed to contain a large amount of invisible mass, which Zwicky termed dunkel Materie, or dark matter. Zwicky's discovery was initially met with skepticism, but over the following decades, evidence for dark matter accumulated from multiple independent sources. In the 1970s, the American astronomer Vera Rubin conducted detailed studies of the rotation curves of spiral galaxies, measuring how fast stars orbited at different distances from the galactic center. She found that stars in the outer regions of galaxies were moving much faster than expected based on the visible mass alone. This could only be explained if galaxies were embedded in extended halos of invisible matter that provided additional gravitational pull. By the 1980s, the existence of dark matter was widely accepted, and theorists began developing detailed models of how dark matter halos form and evolve. These models, based on computer simulations of cosmic structure formation, made specific predictions about the properties and abundance of dark matter halos at different mass scales. Crucially, they predicted that many small halos should exist that might not contain visible galaxies, either because they were too small to retain gas or because various physical processes had prevented star formation. The search for these predicted dark halos took several forms. One approach was to look for their gravitational effects on background objects, a technique called gravitational lensing. When light from a distant galaxy passes near a massive foreground object, the gravitational field of that object bends the light, distorting and magnifying the background image. By carefully analysing these distortions, astronomers can map the distribution of mass in the foreground, including mass that produces no light of its own. Gravitational lensing studies have revealed numerous examples of dark matter concentrations that do not correspond to visible galaxies. Some of these may be dark galaxies in the strictest sense, massive dark matter halos with little or no luminous content. However, interpreting lensing signals is complicated, and it can be difficult to distinguish between a true dark galaxy and other explanations, such as a concentration of dark matter within a larger structure. A more direct approach to finding dark galaxies emerged from radio astronomy. While dark galaxies may lack stars, many of them contain hydrogen gas, which can be detected through its radio emission. The 21 centimetre line of neutral hydrogen is a particularly useful diagnostic because it can penetrate dust and is not affected by the presence or absence of stars. A dark matter halo containing hydrogen but no stars would be invisible to optical telescopes, but could potentially be detected as a radio source. In the early 2000s, several research teams began conducting systematic surveys for hydrogen-rich objects that lacked optical counterparts. These surveys used large radio telescopes to scan regions of the sky, looking for the characteristic signature of neutral hydrogen emission. The goal was to identify gas clouds that might represent dark galaxies, objects with substantial hydrogen content but no detectable stellar populations. One of the most significant early results came from observations of the Virgo cluster, the nearest large galaxy cluster to the Milky Way. In 2005, astronomers using the Arecibo radio telescope in Puerto Rico announced the discovery of a massive hydrogen cloud in the Virgo cluster that appeared to have no optical counterpart. This object, designated Virgo He21, contained about 100 million solar masses of hydrogen gas spread across a region roughly 50,000 light-years in diameter. Despite this substantial gas content, deep optical imaging revealed no stars associated with the cloud. Virgo He21 was hailed as a potential dark galaxy, a massive object dominated by dark matter, with a significant gas reservoir, but no stellar population. The discovery generated considerable excitement in the astronomical community and sparked intense follow-up observations. However, subsequent studies revealed a more complicated picture. The hydrogen cloud appeared to be connected to a nearby spiral galaxy, NGC 4254, by a faint bridge of gas. This suggested that Virgo He21 might not be an independent dark galaxy, but rather debris from a gravitational interaction between NGC 42524 and another object. The case of Virgo He21 illustrates the challenges inherent in identifying dark galaxies. Because these objects are defined by what they lack, it can be difficult to distinguish them from other phenomena that might produce similar observational signatures. Tidal debris from galaxy interactions, gas stripped from normal galaxies by environmental processes, and even instrumental artifacts can all masquerade as dark galaxies if observations are not sufficiently detailed. Despite these challenges, the search for dark galaxies continued and eventually yielded more convincing candidates. One particularly important discovery came from the Arecibo Legacy Fast Alpha Survey, known as ALFALPHA, which systematically mapped neutral hydrogen across large areas of the sky. This survey identified numerous hydrogen sources without obvious optical counterparts, some of which appeared to be genuine dark galaxies rather than tidal debris or other contaminants. Among the most intriguing objects found by ALFALPHA and similar surveys were the so-called almost dark galaxies, objects that contain some stars, but far fewer than would be expected given their hydrogen content and inferred dark matter masses. These objects occupy an intermediate regime between completely dark galaxies and normal star-forming systems, providing valuable insights into the processes that regulate star formation in low-density environments. The discovery of ultra-diffuse galaxies, which we will explore in detail later, represented another major advance in our understanding of dark and dim galactic systems. These objects were first identified in significant numbers in 2015 when astronomers using the Dragonfly telephoto array, a specialized instrument designed to detect extremely faint, extended objects, found dozens of large dim galaxies in the Coma cluster. Ultra-diffuse galaxies have the physical sizes of large spirals like the Milky Way, but contain far fewer stars, making them extremely difficult to detect with conventional telescopes. The Dragonfly discoveries sparked a revolution in the study of low-surface brightness galaxies. Astronomers realized that traditional surveys had been systematically missing a large population of dim, extended objects because their light was spread too thinly to register above the background noise. New surveys optimized for detecting these faint systems have since found ultra-diffuse galaxies in a wide variety of environments, from dense galaxy clusters to isolated regions of the cosmic web. Some ultra-diffuse galaxies appear to be dark matter dominated to an extreme degree, with mass-to-light ratios suggesting that dark matter makes up more than 99% of their total mass. Others, paradoxically, seem to contain very little dark matter at all, challenging our understanding of how such objects could form and survive. This diversity suggests that ultra-diffuse galaxies arise through multiple formation pathways, some related to dark galaxy formation and others involving different physical processes. The advent of new observational facilities has accelerated the pace of discovery. The Atacama Large Millimeter Array, known as ALMA, has enabled detailed studies of molecular gas in dark and dim galaxies, revealing the cold, dense material from which stars might eventually form. The Very Large Array in New Mexico continues to provide high-resolution maps of neutral hydrogen in nearby systems, and space-based observatories like the Hubble Space Telescope have pushed to ever fainter detection limits, revealing stellar populations in objects previously thought to be completely dark. Looking to the future, several upcoming facilities promise to transform our understanding of dark galaxies. The Square Kilometre Array, currently under construction in Australia and South Africa, will be the world's largest radio telescope and will be capable of detecting hydrogen in galaxies across cosmic time. The Vera C. Rubin Observatory, scheduled to begin operations soon, will conduct the most comprehensive optical survey ever attempted, potentially revealing millions of low-surface brightness objects that have escaped previous detection. And the James Webb Space Telescope, already operational, is providing unprecedented views of faint, distant galaxies that may include dark galaxy progenitors in the early universe. The story of dark galaxy discovery is thus far from complete. Each new generation of instruments reveals objects that were previously invisible, expanding our census of the galactic population and challenging our theoretical models. What we have learned so far suggests that dark galaxies are not rare anomalies, but a significant component of the cosmic inventory, one that we are only beginning to properly account for. The journey from Zwicky's initial recognition of dark matter to our current understanding of dark galaxies spans nearly a century of astronomical progress. It is a testament to human curiosity and ingenuity that we have found ways to detect objects that, by their very nature, do not want to be seen. And it is a reminder that the universe always has more secrets to reveal to those patient and clever enough to look for them. As you rest and let these ideas settle in your mind, consider the remarkable fact that we live in an era when such discoveries are possible. Our ancestors could only wonder at the lights in the sky, but we have developed the tools and techniques to probe the darkness between those lights, to find structure and meaning in the apparent void. The dark galaxies that hide throughout the cosmos are no longer completely hidden. Slowly, carefully, we are mapping the invisible architecture of the universe, one faint detection at a time. To truly understand dark galaxies, we must delve deeper into the nature of dark matter itself, the mysterious substance that provides the gravitational foundation for these invisible structures. Dark matter is one of the most profound puzzles in modern physics, a substance that makes up the majority of matter in the universe, yet remains stubbornly resistant to direct detection. Its story is intimately intertwined with the story of dark galaxies, and understanding one requires understanding the other. The evidence for dark matter comes from multiple independent lines of observation, each pointing to the same conclusion. The visible matter we can see accounts for only a small fraction of the gravitational mass present in the universe. We have already mentioned the rotation curves of spiral galaxies, which show that stars in the outer regions orbit faster than they should, based on the visible mass alone. But this is just one piece of a much larger puzzle. On the scale of galaxy clusters, the evidence is equally compelling. When we measure the velocities of galaxies within clusters, we find that they are moving too fast to be gravitationally bound by the visible matter alone. The clusters should fly apart, yet they remain intact, held together by the gravity of unseen mass. X-ray observations of hot gas within clusters tell the same story. The gas is too hot, moving too fast to be confined by the gravity of the visible galaxies. Something else must be providing the necessary gravitational pull. Gravitational lensing provides yet another line of evidence. When we map the distribution of mass in galaxy clusters by analysing how they bend the light from background galaxies, we find that the mass is distributed differently than the visible matter. The dark matter forms a smooth extended halo that surrounds and permeates the cluster, while the visible galaxies are concentrated in specific locations within this halo. In some cases, collisions between galaxy clusters have separated the dark matter from the ordinary matter, providing dramatic visual evidence that these are distinct components. Perhaps the most compelling evidence for dark matter comes from the cosmic microwave background, the faint afterglow of the Big Bang that fills the universe. This radiation carries an imprint of conditions in the early universe, including tiny fluctuations in density that would eventually grow into galaxies and galaxy clusters. The pattern of these fluctuations depends sensitively on the composition of the universe, and detailed measurements by satellites like COBE, WMAP, and Planck have shown that dark matter must be present in roughly the amounts predicted by other observations. All of this evidence tells us that dark matter exists, but it tells us frustratingly little about what dark matter actually is. We know that it interacts gravitationally, because that is how we detect its presence. We know that it does not interact significantly with light, because otherwise we would see it. And we know that it does not interact strongly with ordinary matter through the electromagnetic or strong nuclear forces, because otherwise we would have detected it in laboratory experiments. These constraints have led physicists to propose various candidates for dark matter particles. The leading candidates for many years were weakly interacting massive particles, known as WIMPs, hypothetical particles that would interact through the weak nuclear force and gravity, but not through electromagnetism or the strong force. WIMPs were attractive candidates because they arose naturally in certain extensions of the standard model of particle physics, and because they would have been produced in the right amounts in the early universe to account for the observed dark matter density. However, decades of increasingly sensitive experiments have failed to detect WIMPs directly, leading many researchers to consider alternative candidates. Axions, originally proposed to solve a different problem in particle physics, have gained attention as potential dark matter particles. Primordial black holes, formed in the very early universe, represent another possibility. And more exotic proposals, including particles from hidden sectors that interact with ordinary matter only through gravity, continue to be explored. The nature of dark matter has important implications for the properties of dark matter halos, and by extension, for dark galaxies. Different dark matter candidates would produce halos with different density profiles, different shapes, and different amounts of substructure. By studying the properties of dark galaxies and other dark matter-dominated systems, astronomers hope to constrain the nature of dark matter itself. One key prediction of the standard cold dark matter model is that dark matter halos should have a characteristic density profile, with density increasing steeply toward the center. This profile, often called the NFW profile after the researchers who first described it, has been tested extensively through observations of galaxies and galaxy clusters. The results have been mixed. Some observations support the NFW profile, while others suggest that the central regions of halos may be less dense than predicted, a discrepancy sometimes called the core cusp problem. Dark galaxies offer a unique opportunity to test these predictions because they are dominated by dark matter to an even greater extent than normal galaxies. Without significant amounts of ordinary matter to complicate the picture, the gravitational dynamics of dark galaxies should be determined almost entirely by their dark matter halos. By measuring the velocities of any gas or stars present in these systems, astronomers can map the distribution of dark matter and compare it to theoretical predictions. Another important prediction of cold dark matter models is that large halos should contain numerous smaller subhalos, remnants of the smaller structures that merge together to form the larger halo. These subhalos would themselves be potential sites for dark galaxy formation. The number and distribution of subhalos predicted by simulations can be compared to the observed population of satellite galaxies around large galaxies like the Milky Way. For many years, there appeared to be a significant discrepancy between the predicted and observed numbers of satellite galaxies. Simulations predicted far more subhalos than the number of known satellite galaxies, a problem known as the missing satellites problem. This discrepancy could be explained if many subhalos exist, but fail to form visible galaxies, essentially becoming dark satellites. Alternatively, it could indicate that our understanding of dark matter or galaxy formation is incomplete. Recent discoveries have complicated this picture. Improved surveys have found many more faint satellite galaxies around the Milky Way and other nearby systems, reducing the apparent discrepancy. At the same time, simulations have become more sophisticated, incorporating the effects of baryonic physics on dark matter halo structure. The current consensus is that the missing satellites problem is largely resolved, though uncertainties remain. The relationship between dark matter halos and the galaxies that form within them is governed by complex physical processes that we are still working to understand. When ordinary matter falls into a dark matter halo, it must lose energy to settle into the center and eventually form stars. This energy loss occurs primarily through radiative cooling, as the gas emits photons and gradually cools down. The efficiency of this cooling depends on the temperature and density of the gas, as well as its chemical composition. In small dark matter halos, the gravitational potential is shallow, and gas can easily escape if it is heated by energetic processes. Ultraviolet radiation from the first stars and galaxies, produced during the epoch of rhyonisation in the early universe, would have heated the intergalactic medium and prevented gas from falling into small halos. This provides one explanation for why small halos might remain dark. They simply could not accumulate enough gas to form stars. In larger halos, the situation is more complicated. These systems have deep gravitational wells, capable of capturing and retaining substantial quantities of gas, even in the presence of heating. Yet we observe dark galaxies with masses comparable to the Milky Way, systems that should have had no difficulty accumulating baryonic matter. Something else must be preventing star formation in these objects, and understanding what that something is remains an active area of research. One possibility involves the angular momentum of the infalling gas. As gas falls into a dark matter halo, it typically carries angular momentum that causes it to settle into a rotating disk rather than collapsing directly to the center. If the angular momentum is particularly high, the resulting disk may be very extended and have low surface density, making it difficult for the gas to reach the densities required for star formation. This could produce a large gas-rich system with very few stars, essentially a dark galaxy with a diffuse hydrogen disk. Another possibility involves feedback processes that regulate star formation. Even if some stars do manage to form, they can inject energy into their surroundings through stellar winds, supernova explosions, and radiation pressure. This energy can heat the surrounding gas and drive it out of the galaxy, preventing further star formation. In extreme cases, a single burst of star formation might be sufficient to expel most of the gas from a low-mass system, leaving behind a dark remnant. The role of supermassive black holes adds another layer of complexity. Many galaxies, perhaps all sufficiently massive ones, harbour supermassive black holes at their centres. When matter falls onto these black holes, it can release tremendous amounts of energy, far more than stellar processes alone. This energy, known as active galactic nucleus feedback, can heat and expel gas on galactic scales, potentially quenching star formation entirely. A dark matter halo that formed a supermassive black hole early in its history might have had its star formation shut down before it could produce a significant stellar population. The interplay between these various processes creates a rich landscape of possible outcomes. Some dark matter halos become bright, actively star-forming galaxies. Others form some stars, but then have their star formation quenched by feedback or environmental effects. Still others never form significant numbers of stars at all, remaining dark throughout cosmic history. The relative importance of different processes likely varies with halo mass, environment, and cosmic epoch, producing the diversity of dark and dim galaxies we observe today. Understanding this diversity requires combining observations with theoretical models and numerical simulations. Modern cosmological simulations can follow the evolution of dark matter and baryonic matter together, tracking how gas flows into halos, cools, and forms stars. These simulations have become increasingly sophisticated, incorporating ever more detailed treatments of the relevant physical processes. By comparing simulated galaxy populations to observations, researchers can test their understanding and identify areas where the models need improvement. One important insight from simulations is that the relationship between dark matter halo mass and stellar mass is not a simple one-to-one correspondence. At both the low mass and high mass ends, the efficiency of star formation drops significantly. Low mass halos lose their gas to heating and feedback, while high mass halos have their star formation suppressed by active galactic nucleus feedback. The result is that the stellar mass of a galaxy is a poor predictor of its total mass and vice versa. This insight has important implications for dark galaxies. If we identify an object based on its stellar content alone, we may be severely underestimating its true mass. Conversely, if we identify a dark matter halo based on its gravitational effects, we cannot assume that it will contain a proportionate stellar population. The dark galaxies we observe may represent the extreme tail of a continuous distribution, systems where the efficiency of star formation was particularly low for one reason or another. The connection between dark matter and dark galaxies also raises intriguing questions about the role of dark matter in cosmic evolution. Dark matter halos are the sites where galaxies form, but they are also the sites where galaxies fail to form. The balance between these outcomes depends on the properties of dark matter, the physics of baryonic matter, and the environmental conditions in different parts of the universe. By studying dark galaxies, we gain insight into all of these factors and their complex interactions. As our understanding of dark matter continues to evolve, so too will our understanding of dark galaxies. Future experiments may finally detect dark matter particles directly, revealing their nature and allowing us to make more precise predictions about halo properties. Future observations will discover more dark galaxies and characterize their properties in greater detail, and future simulations will incorporate ever more realistic physics, providing a clearer picture of how dark matter halos give rise to the full spectrum of galactic outcomes. For now, dark matter remains the invisible architect of cosmic structure, shaping the universe on the largest scales while eluding our direct detection. Dark galaxies are among its most intriguing creations, structures that exist in the shadow of their luminous counterparts, testifying to the complexity and subtlety of the processes that govern galaxy formation. As you drift towards sleep, consider that most of the matter in the universe is invisible, that most of the structure is hidden, and that we are only beginning to map the true architecture of the cosmos. Now that we have established the theoretical framework for understanding dark galaxies, let us turn our attention to some specific examples. These case studies will illustrate the diversity of dark galaxy phenomena and the various methods astronomers use to detect and characterize these elusive objects. Each of these galaxies has its own story to tell, its own mysteries to unravel, and its own lessons to teach us about the nature of the universe. Virgo He21, the controversial pioneer. We begin with Virgo He21, the object that first brought dark galaxies to widespread attention in the astronomical community. Discovered in 2005 through observations with the Arecibo radio telescope, Virgo He21 appeared to be a massive cloud of neutral hydrogen in the Virgo cluster with no visible stellar counterpart. The discovery team estimated that the cloud contained approximately 100 million solar masses of hydrogen gas, spread across a region roughly 50,000 light-years in diameter. What made Virgo He21 particularly intriguing was the evidence for rotation within the gas cloud. Radio observations revealed a velocity gradient across the cloud, suggesting that it was spinning like a disk. From this rotation, astronomers could estimate the total mass needed to gravitationally bind the system, and the result was startling. The inferred mass was roughly 10 billion solar masses, about 100 times more than the detected hydrogen. This implied that Virgo He21 was embedded in a massive dark matter halo, making it a strong candidate for a genuine dark galaxy. The discovery generated considerable excitement, but also controversy. Follow-up observations revealed a faint bridge of hydrogen connecting Virgo He21 to a nearby spiral galaxy, NGC 4254. This raised the possibility that Virgo He21 was not an independent dark galaxy, but rather tidal debris, gas that had been stripped from NGC 4254 during a gravitational interaction with another object. The debate over the nature of Virgo He21 continued for years. Some researchers argued that the rotation pattern and mass estimates were consistent with an independent dark matter halo, while others maintained that the connection to NGC 4254 indicated a tidal origin. Deep optical imaging failed to reveal any stellar population associated with the hydrogen cloud, supporting the dark galaxy interpretation. But the proximity to NGC 4254 and the connecting gas bridge remain troubling. Current consensus leans toward a hybrid explanation. Virgo He21 may represent gas that was tidally stripped from NGC 4254, but that subsequently fell into an independent dark matter halo. This would explain both the connection to the spiral galaxy and the evidence for a massive dark matter component. Alternatively, the dark matter halo may have triggered the tidal interaction in the first place, its gravitational influence disturbing NGC 4254 and pulling gas out into the observed configuration. Regardless of its ultimate origin, Virgo He21 played a crucial role in stimulating interest in dark galaxies and demonstrating the potential of radio observations for detecting these objects. It showed that massive hydrogen clouds without stellar counterparts do exist and that they can contain dynamical evidence for substantial dark matter content. Even if Virgo He21 itself turns out to be more complicated than initially thought, it opened the door to a new field of research. Dragonfly 44, the dark giant. Among the most remarkable dark galaxies discovered in recent years is Dragonfly 44, an ultra-diffuse galaxy in the Coma cluster that has captured the imagination of astronomers and the public alike. Discovered in 2015 using the Dragonfly telephoto array, this ghostly object has the physical size of the Milky Way, but contains only about 1% as many stars. Its surface brightness is so low that it is barely detectable, even with specialized instruments designed to find faint, extended objects. What makes Dragonfly 44 particularly extraordinary is its inferred dark matter content. By measuring the velocities of globular clusters orbiting the galaxy, astronomers estimated its total mass at roughly 1 trillion solar masses, comparable to the mass of the Milky Way. Yet its stellar mass is only about 300 million solar masses, implying that dark matter makes up more than 99% of the galaxy's total mass. This is an extreme mass-to-light ratio, far higher than typical galaxies. The discovery of Dragonfly 44 raised profound questions about galaxy formation. How could an object with the dark matter halo of a major galaxy end up with so few stars? What physical processes could produce such an extreme outcome? And how many similar objects might be lurking undetected in the cosmic darkness? Several hypotheses have been proposed to explain Dragonfly 44. One possibility is that it formed in an unusual environment where gas was unable to cool and condense efficiently. Perhaps it was located in a region of the early universe where heating from external sources prevented star formation. Or perhaps its gas had unusually high angular momentum that prevented collapse. Another possibility is that Dragonfly 44 did form stars early in its history, but then had its star formation quenched by some catastrophic event, such as a burst of feedback from a central black hole or a violent interaction with another galaxy. The globular cluster population of Dragonfly 44 provides important clues. The galaxy contains an unusually large number of globular clusters for its stellar mass, roughly 100 compared to the handful that would be expected for a galaxy of its luminosity. This suggests that Dragonfly 44 may have formed its globular clusters during an early, intense phase of star formation that was subsequently shut down. The globular clusters survived while the broader stellar population failed to develop. Subsequent observations of Dragonfly 44 have refined our understanding of this enigmatic object. Spectroscopic studies have confirmed the high-velocity dispersion of its globular clusters, supporting the estimate of a massive dark matter halo. Deep imaging has revealed the faint, diffuse stellar population in greater detail, showing a smooth, featureless distribution without the spiral arms or other structures seen in normal galaxies of similar mass. Dragonfly 44 has become a benchmark object for studies of dark matter-dominated galaxies. Its extreme properties make it an ideal laboratory for testing theories of dark matter and galaxy formation. Ongoing observations continue to probe its structure and dynamics, seeking to understand how such an unusual object came to exist. NGC 1052, DF2 and DF4, the dark matter deficient puzzles. While most dark galaxies are defined by an excess of dark matter relative to their stellar content, a pair of ultra-diffuse galaxies discovered in 2018 presented the opposite puzzle. NGC 1050 DF2 and NGC 1052 DF4, both associated with the elliptical galaxy NGC 1052, appeared to contain very little dark matter at all. These discoveries challenged our understanding of galaxy formation and sparked intense debate in the astronomical community. The initial observations of NGC 1052 DF2 suggested that its globular clusters were moving too slowly to be embedded in a significant dark matter halo. The velocity dispersion was consistent with the gravitational influence of the visible stars alone, implying that dark matter contributed little to the galaxy's total mass. If confirmed, this would make NGC 1052 DF2 a galaxy almost entirely devoid of dark matter, a seemingly impossible object given our understanding of how galaxies form. The discovery was controversial from the start. Some researchers questioned the measurements, arguing that the small sample of globular clusters and the uncertainties in the velocity measurements could not reliably constrain the dark matter content. Others questioned the distance to the galaxy, noting that if NGC 1052 DF2 were closer than initially estimated, its inferred properties would change significantly. Subsequent observations have largely supported the original findings, though with some modifications. The distance controversy has been partially resolved, with most studies now agreeing that NGC 1052 DF2 is indeed associated with NGC 1052 and lies at a distance of roughly 60 million light-years. The velocity dispersion measurements have been refined and remain consistent with a low dark matter content, though the exact amount of dark matter present is still debated. The discovery of NGC 1052 DF4, a second dark matter deficient galaxy in the same system, strengthened the case that these objects are real and not the result of measurement errors. Finding two such galaxies in the same environment suggested that whatever process created them might be related to their location near the massive elliptical NGC 1052. Several theories have been proposed to explain dark matter-deficient galaxies. One possibility is that they formed from gas that was expelled from NGC 1052 during a past interaction or merger event. This gas would have carried little dark matter with it, since dark matter does not interact through the electromagnetic forces that cause gas to be expelled. Stars forming from this gas would therefore inherit its low dark matter content. Another possibility involves tidal stripping. If these galaxies were once normal, dark matter-dominated systems, close passages by NGC 1052 could have stripped away their dark matter halos while leaving their stellar components relatively intact. Dark matter halos extend far beyond the visible parts of galaxies and would be more susceptible to tidal forces than the more compact stellar distributions. A third possibility is that these galaxies represent a new formation pathway that we do not yet fully understand. Perhaps certain conditions in the early universe allowed galaxies to form without significant dark matter, or perhaps our understanding of dark matter itself is incomplete in ways that allow for such objects. The existence of dark matter-deficient galaxies has important implications for theories of dark matter. Some alternative theories of gravity proposed to explain galactic dynamics without invoking dark matter struggle to account for these objects. If gravity behaves differently than Einstein predicted on galactic scales, as these theories suggest, then all galaxies should show similar deviations from Newtonian expectations. The fact that some galaxies appear to lack dark matter while others are dominated by it is more naturally explained if dark matter is a real substance that can be present in varying amounts. NGC 1052 DF2 and DF4 thus provide a fascinating counterpoint to galaxies like Dragonfly 44. Together, they demonstrate the remarkable diversity of galactic systems and the complex interplay of processes that determine how much dark matter a galaxy contains. They remind us that the universe is full of surprises, and that our theories must be flexible enough to accommodate the unexpected. H1-1232 plus 20, a lonely cloud in the void. Moving away from galaxy clusters, we encounter HI-1232 plus 20, a dark galaxy candidate discovered in a much more isolated environment. This object was identified through the Alfalfa survey as a hydrogen cloud with no obvious optical counterpart. Located in a relatively empty region of space far from any major galaxy or cluster, the isolation of HI-1232 plus 20 makes it particularly interesting because it rules out many of the complicating factors that affect dark galaxy candidates in dense environments. There is no nearby massive galaxy from which gas could have been tidally stripped. There is no cluster medium that could have influenced its evolution. Whatever HI-1232 plus 20 is, it appears to have formed and evolved in relative isolation. Observations of HI-1232 plus 20 reveal a hydrogen mass of roughly 1 billion solar masses, making it a substantial gas reservoir. The gas shows evidence of rotation, suggesting that it is gravitationally bound and embedded in a dark matter halo. Deep optical imaging has failed to detect any stellar population, placing stringent upper limits on the number of stars present. The properties of HI-1232 plus 20 are consistent with theoretical predictions for dark galaxies that fail to form stars due to insufficient cooling or excessive angular momentum. Its isolation suggests that it has not been significantly affected by environmental processes and may represent a relatively pristine example of a dark matter halo that never ignited star formation. However, the interpretation of HI-1232 plus 20 remains uncertain. The possibility that it is a tidal remnant from an ancient interaction cannot be entirely ruled out, even in its isolated location. Galaxies can travel significant distances over cosmic time, and a gas cloud stripped from a galaxy billions of years ago might now appear isolated, even if it had a tidal origin. Ongoing observations of HI-1232 plus 20 and similar objects aim to better characterize their properties and constrain their origins. Radio interferometry can map the distribution and kinematics of the hydrogen in greater detail, while deeper optical imaging may eventually detect faint stellar populations that current observations have missed. These studies will help determine whether HI-1232 plus 20 is a genuine dark galaxy or something else entirely. Coma cluster ultra-diffuse galaxies, a population revealed. The Coma cluster has proven to be a particularly rich hunting ground for dark and dim galaxies. Beyond individual objects, like Dragonfly 44, systematic surveys have revealed a large population of ultra-diffuse galaxies in this massive cluster, providing statistical insights into the properties and origins of these systems. The Dragonfly Telephoto Array Survey of the Coma cluster identified 47 ultra-diffuse galaxies in a single observing campaign, demonstrating that these objects are far more common than previously recognized. Subsequent surveys using other instruments have expanded this census, revealing hundreds of ultra-diffuse galaxies in Coma and other clusters. The ultra-diffuse galaxies in the Coma cluster span a range of properties. Some, like Dragonfly 44, appear to be extremely dark matter-dominated, with mass-to-light ratios far exceeding those of normal galaxies. Others have more modest dark matter content, falling closer to the range seen in typical dwarf galaxies. This diversity suggests that ultra-diffuse galaxies arise through multiple formation pathways and are not a homogeneous population. The spatial distribution of ultra-diffuse galaxies within the Coma cluster provides clues to their origins. Some are found near the cluster center, where tidal forces and interactions with the hot intracluster medium would be strongest. Others are located in the cluster outskirts, where environmental effects would be weaker. The presence of ultra-diffuse galaxies throughout the cluster suggests that both environmental and internal processes contribute to their formation. Studies of the stellar populations in Coma cluster ultra-diffuse galaxies reveal generally old ages and low metallicities, consistent with star formation that occurred early in cosmic history and then ceased. This supports scenarios in which these galaxies formed their stars in a brief early phase before having their star formation quenched by feedback or environmental effects. The globular cluster populations of ultra-diffuse galaxies in Coma vary widely. Some have abundant globular cluster systems, like Dragonfly 44, while others have few or no detectable globular clusters. This variation may reflect differences in formation history, with globular cluster-rich systems having experienced more intense early star formation. The Coma cluster ultra-diffuse galaxy population has become a key resource for understanding dark and dim galaxies. By studying these objects statistically, astronomers can move beyond individual case studies to identify trends and correlations that reveal the underlying physics. The large sample size allows for meaningful comparisons between different subpopulations and different theoretical predictions. Andromeda's dark companions. Our own cosmic neighbourhood also contains intriguing dark galaxy candidates. The Andromeda Galaxy, the nearest large spiral to the Milky Way, is surrounded by a retinue of satellite galaxies, some of which push the boundaries of what we consider a galaxy. Among the faintest known galaxies are several satellites of Andromeda discovered in recent surveys. Objects like Andromeda 19 and Andromeda 21 have such low surface brightness and so few stars that they were only detected through careful analysis of resolved stellar populations. These galaxies contain perhaps a few 100,000 stars spread across regions thousands of light years in diameter, giving them surface brightnesses barely above the detection threshold. The dark matter content of these faint Andromeda satellites is difficult to measure directly, but indirect evidence suggests they are highly dark matter dominated. Their survival in the tidal environment of Andromeda requires substantial dark matter halos to provide gravitational binding. Without dark matter, these diffuse stellar systems would have been torn apart long ago by Andromeda's gravitational influence. The discovery of ever fainter satellites around Andromeda and the Milky Way has implications for the missing satellite problem discussed earlier. Each new detection reduces the apparent discrepancy between predicted and observed satellite numbers, suggesting that many small dark matter halos do host visible galaxies, albeit extremely faint ones. However, the faintest satellites detected so far may still represent only the tip of the iceberg, with an even larger population of completely dark satellites remaining undetected. The local group, comprising the Milky Way, Andromeda, and their satellites, thus serves as a laboratory for studying dark and dim galaxies in unprecedented detail. The proximity of these objects allows for resolved observations of individual stars, providing information about stellar populations, star formation histories, and chemical evolution that cannot be obtained for more distant systems. As we continue our journey through the realm of dark galaxies, these case studies illustrate the remarkable diversity of objects that fall under this broad category. From massive isolated hydrogen clouds to ultra-diffuse galaxies in dense clusters, from dark matter-dominated giants to puzzling dark matter-deficient systems, the dark galaxy phenomenon encompasses a wide range of physical situations and formation pathways. Each new discovery adds to our understanding and raises new questions, driving the ongoing exploration of the invisible universe. Among the most fascinating categories of dark and dim galaxies are the ultra-diffuse galaxies, a class of objects that has revolutionized our understanding of galactic diversity since their recognition as a distinct population in 2015. These ghostly giants occupy a unique niche in the galactic zoo, combining the physical sizes of large spiral galaxies with the luminosities of tiny dwarf galaxies. Their discovery has opened new windows onto the processes that shape galaxy formation and evolution. Ultra-diffuse galaxies are defined primarily by their low surface brightness, typically less than 24 magnitudes per square arc-second in the optical bands. To put this in perspective, the night sky itself has a surface brightness of around 22 magnitudes per square arc-second, meaning that ultra-diffuse galaxies are only slightly brighter than the background sky. Detecting them requires specialized techniques and instruments optimized for low-surface brightness observations. The physical sizes of ultra-diffuse galaxies are what make them truly remarkable. Despite their faintness, many of these objects have effective radii of several kiloparsecs, comparable to the Milky Way and other large spiral galaxies. A galaxy the size of the Milky Way, but with the luminosity of a dwarf galaxy, is an extraordinary object, one that challenges our intuitions about how galaxies should look. The recognition of ultra-diffuse galaxies as a distinct class emerged from observations with the Dragonfly telephoto array, an innovative instrument designed specifically for detecting faint, extended structures. The Dragonfly array consists of multiple telephoto lenses working together as a single telescope, with specialized coatings that minimize scattered light and enable detection of extremely low surface brightness features. When the Dragonfly team turned their instrument toward the Coma cluster in 2015, they discovered dozens of large, faint galaxies that had been overlooked by previous surveys. These objects were hiding in plain sight. Their light spread so thinly that conventional telescopes had missed them entirely. The discovery paper sparked immediate interest in the astronomical community and launched a new field of research. Subsequent surveys have found ultra-diffuse galaxies in a wide variety of environments. They are abundant in galaxy clusters like Coma and Virgo, where hundreds have now been catalogued. They are found in galaxy groups, including the local group and nearby groups like Centaurus A, and they are found in isolation, far from any large galaxy or cluster, demonstrating that their formation does not require a dense environment. The diversity of environments where ultra-diffuse galaxies are found suggests that multiple formation pathways may be at work. In cluster environments, tidal interactions and ram pressure stripping could transform normal galaxies into ultra-diffuse systems by removing gas and puffing up stellar distributions. In isolation, internal processes like feedback from star formation or unusual initial conditions might produce similar outcomes through different mechanisms. Several theoretical models have been proposed to explain the origin of ultra-diffuse galaxies. One class of models invokes high angular momentum, suggesting that these galaxies formed from gas with unusually high spin that settled into extended, low-density disks. Star formation in such disks would be inefficient, producing few stars spread across large areas and resulting in the observed low surface brightness. Another class of models involves feedback-driven expansion. In this scenario, ultra-diffuse galaxies initially formed as more compact systems, but were puffed up by energetic feedback from star formation. Supernova explosions and stellar winds inject energy into the interstellar medium, driving gas outflows that can also affect the distribution of stars. If this feedback is particularly strong or occurs at a critical time in the galaxy's evolution, it might expand the stellar distribution to ultra-diffuse proportions. A third possibility involves tidal heating and stripping in dense environments. Galaxies falling into clusters experience strong tidal forces that can strip away their outer regions and heat their stellar orbits. This process, known as tidal stirring, can transform compact dwarf galaxies into more extended diffuse systems. The prevalence of ultra-diffuse galaxies in clusters supports this mechanism, though it cannot explain isolated ultra-diffuse galaxies that have never experienced a cluster environment. Failed massive galaxies represent yet another proposed formation pathway. In this scenario, ultra-diffuse galaxies are the remnants of dark matter halos that had the potential to become large spiral galaxies, but had their star formation truncated early in cosmic history. Perhaps they lost their gas to reionization, or perhaps early feedback was particularly effective at expelling baryonic matter. The result would be a massive dark matter halo with only a small stellar population, consistent with the properties of objects like Dragonfly 44. The dark matter content of ultra-diffuse galaxies varies dramatically across the population. Some, like Dragonfly 44, appear to be extremely dark matter dominated, with mass-to-light ratios suggesting that more than 99% of their mass is invisible. Others, like NGC 1050 BF2 and DF4, appear to contain very little dark matter. This diversity is puzzling and suggests that ultra-diffuse galaxies do not form through a single mechanism. Understanding the dark matter content of ultra-diffuse galaxies requires measuring their dynamical masses, typically through observations of stellar velocities or the motions of globular clusters. These measurements are challenging because ultra-diffuse galaxies are faint and their stars are difficult to observe spectroscopically. Globular clusters, being more luminous, provide an alternative tracer of the gravitational potential, but many ultra-diffuse galaxies have few or no globular clusters available for study. The globular cluster populations of ultra-diffuse galaxies have attracted considerable attention. Some ultra-diffuse galaxies have remarkably rich globular cluster systems for their stellar masses, with specific frequencies, the number of globular clusters per unit luminosity, far exceeding those of normal galaxies. This suggests that globular cluster formation was particularly efficient in these systems, perhaps during an intense early phase of star formation. The colours and stellar populations of ultra-diffuse galaxies provide clues to their formation histories. Most ultra-diffuse galaxies in clusters have red colours and old stellar populations, indicating that their star formation ceased long ago. This is consistent with scenarios in which they formed their stars early and then had their star formation quenched by environmental effects or feedback. However, some ultra-diffuse galaxies, particularly those in isolated environments, show bluer colours and evidence for more recent star formation. The spatial distribution of ultra-diffuse galaxies within clusters reveals patterns that constrain their origins. In the Coma cluster, ultra-diffuse galaxies are found throughout the cluster volume, but are more concentrated toward the centre than the overall galaxy population. This suggests that they have been in the cluster for a long time and have had their orbits affected by dynamical friction. However, the presence of ultra-diffuse galaxies in the cluster outskirts indicates that not all of them are ancient cluster members. The relationship between ultra-diffuse galaxies and other galaxy types remains an active area of research. Are ultra-diffuse galaxies simply the low-surface brightness tail of the normal galaxy population, or do they represent a distinct class with different formation physics? The answer may depend on which ultra-diffuse galaxies we consider, with different subpopulations having different origins. Comparisons between ultra-diffuse galaxies and normal dwarf galaxies reveal both similarities and differences. In terms of stellar mass, many ultra-diffuse galaxies overlap with the dwarf galaxy regime. However, their sizes are much larger and their surface brightnesses are much lower. Some researchers have suggested that ultra-diffuse galaxies are simply puffed-up dwarfs, while others argue that their extreme properties require distinct formation mechanisms. The connection between ultra-diffuse galaxies and dark galaxies is intimate but complex. Ultra-diffuse galaxies are not completely dark. They do contain stars, but some of them are so dark matter-dominated that they approach the dark galaxy regime. The most extreme ultra-diffuse galaxies with mass-to-light ratios in the thousands are essentially dark galaxies with a thin frosting of stars. Less extreme ultra-diffuse galaxies shade into the normal galaxy population without a clear boundary. Observational selection effects complicate our understanding of the ultra-diffuse galaxy population. Because these objects are so faint, we can only detect them in relatively nearby regions of the universe. More distant ultra-diffuse galaxies fall below our detection thresholds, meaning that our census is necessarily incomplete. The true abundance of ultra-diffuse galaxies and their contribution to the overall galaxy population remains uncertain. Future surveys with next-generation facilities will dramatically expand our knowledge of ultra-diffuse galaxies. The Vera C. Rubin Observatory, with its unprecedented combination of depth and sky coverage, will detect ultra-diffuse galaxies across large volumes of the nearby universe. The James Webb Space Telescope will probe the stellar populations of ultra-diffuse galaxies in detail, revealing their star formation histories and chemical evolution. And the next generation of extremely large ground-based telescopes will enable spectroscopic studies of individual stars in nearby ultra-diffuse galaxies. As you rest and let your thoughts drift, consider the ghostly ultra-diffuse galaxies scattered throughout the cosmos. These objects exist at the boundary between visibility and invisibility, their dim glow barely distinguishable from the darkness of space itself. They remind us that the universe contains wonders at every scale and brightness level, from the blazing cores of active galaxies to the faint whispers of ultra-diffuse systems. In their quiet way, they expand our understanding of what a galaxy can be. The search for dark galaxies has driven remarkable advances in astronomical instrumentation and observational techniques. Because these objects are defined by their faintness or invisibility, detecting them requires pushing our technology to its absolute limits and developing creative new approaches to seeing the unseen. In this section, we explore the methods astronomers use to find and study dark galaxies, from radio telescopes to gravitational lensing to specialized optical instruments. Radio observations, listening for hydrogen. Radio astronomy has been central to the search for dark galaxies because it allows us to detect hydrogen gas, which many dark galaxies contain even when they lack stars. The 21 centimeter emission line of neutral hydrogen arises from a quantum mechanical transition in the hydrogen atom and provides a unique signature that can be detected across cosmic distances. When a hydrogen atom is in its ground state, the electron and proton can have their spins aligned either parallel or anti-parallel. The parallel configuration has slightly higher energy, and when the atom transitions from the parallel to the anti-parallel state, it emits a photon with a wavelength of 21 centimeters. This transition is extremely rare for any individual atom, but the vast quantities of hydrogen in galaxies produce detectable emission. Radio telescopes designed to detect 21 centimeter emission have been instrumental in discovering dark galaxy candidates. The Arecibo telescope in Puerto Rico, before its collapse in 2020, was a particularly powerful instrument for this purpose. Its large collecting area made it sensitive to faint hydrogen signals, while its location in a natural limestone sinkhole provided shielding from terrestrial radio interference. The Alfalfa survey, conducted with Arecibo, systematically mapped neutral hydrogen across large areas of the sky. This survey detected over 30,000 hydrogen sources, many of which correspond to known optical galaxies. However, a fraction of the detections lack obvious optical counterparts and represent potential dark galaxy candidates. Follow-up observations of these objects continue to characterize their properties and determine their nature. Radio interferometers provide higher spatial resolution than single-dish telescopes, allowing astronomers to map the distribution of hydrogen within dark galaxy candidates. The Very Large Array in New Mexico and the Westerbork Synthesis Radio Telescope in the Netherlands have been used extensively for this purpose. By combining signals from multiple antennas spread across large baselines, these instruments can resolve structures on scales of arcseconds, revealing the morphology and kinematics of hydrogen clouds. The upcoming Square Kilometre Array will revolutionize radio observations of dark galaxies. This massive facility, currently under construction in Australia and South Africa, will be the most sensitive radio telescope ever built. It will detect hydrogen in galaxies across cosmic time, potentially revealing the evolution of dark galaxies from the early universe to the present day. The SKA will also have the resolution to study the internal structure of dark galaxies in unprecedented detail. One challenge in using radio observations to find dark galaxies is distinguishing genuine dark galaxies from other phenomena that can produce isolated hydrogen clouds. Tidal debris from galaxy interactions, high-velocity clouds falling into galaxies, and even instrumental artifacts can all produce hydrogen signals without optical counterparts. Careful analysis is required to identify the most promising dark galaxy candidates and rule out alternative explanations. Optical and infrared techniques, seeing the faint. While dark galaxies by definition produce little light, many of them do contain some stars, and detecting these faint stellar populations is crucial for understanding their properties. Specialized optical and infrared techniques have been developed to push detection limits to ever fainter levels. The Dragonfly telephoto array represents an innovative approach to low-surface brightness imaging. Rather than using a single large mirror, Dragonfly employs an array of commercial telephoto lenses with specialized nano-fabricated coatings that minimize scattered light. This design is optimized for detecting faint, extended structures that would be lost in the scattered light halos of conventional telescopes. The success of Dragonfly in discovering ultra-diffuse galaxies has inspired similar projects around the world. The Huntsman telescope in Australia and the Condor Array in New Mexico are among the instruments designed with similar philosophies, prioritizing scattered light control over raw collecting area. These facilities are expanding our census of low surface brightness objects and revealing populations that traditional telescopes have systematically missed. Deep imaging with conventional telescopes also plays an important role in studying dark galaxies. By combining many hours of exposure time and carefully controlling systematic errors, astronomers can reach surface brightness levels approaching those achieved by specialized instruments. The Hyper-Suprime Cam on the Subaru telescope and the Dark Energy camera on the Blanco telescope have both been used for deep surveys that have discovered numerous ultra-diffuse and low surface brightness galaxies. Space-based observatories offer advantages for detecting faint objects because they avoid the atmospheric emission and absorption that plague ground-based observations. The Hubble Space Telescope has been used extensively to study dark galaxy candidates, providing high-resolution images that can resolve individual stars in nearby systems. The James Webb Space Telescope, with its unprecedented infrared sensitivity, is opening new windows onto faint stellar populations in dark and dim galaxies. Infrared observations are particularly valuable for studying the stellar content of dark galaxies because older stellar populations, which dominate most dark galaxies, emit much of their light at infrared wavelengths. The red giant stars that are the most luminous members of old populations have surface temperatures that peak in the near infrared, making them easier to detect at these wavelengths than in visible light. Adaptive optics systems on ground-based telescopes can partially compensate for atmospheric distortion, providing sharper images that improve the detection of faint point sources. This technology is particularly useful for identifying globular clusters around dark galaxies which serve as tracers of the gravitational potential and allow dynamical mass measurements. The challenge of detecting dark galaxies in optical and infrared light is fundamentally one of contrast. These objects are faint, and they must be distinguished from the much brighter foreground and background sources that dominate astronomical images. Sophisticated image processing techniques, including careful sky subtraction and modelling of scattered light, are essential for revealing the faint glow of dark galaxy stellar populations. Gravitational lensing, weighing the invisible. Gravitational lensing provides a powerful method for detecting dark matter structures, regardless of whether they contain any luminous matter. When light from a distant source passes near a massive foreground object, the gravitational field of that object bends the light, distorting and magnifying the background image. By analysing these distortions, astronomers can map the distribution of mass in the foreground, including mass that produces no light of its own. Strong gravitational lensing occurs when the foreground mass is sufficiently concentrated to produce dramatic distortions, including multiple images of the background source or extended arcs of stretched light. Galaxy clusters are the most common strong lenses, and studies of cluster lensing have revealed dark matter distributions that do not always correspond to the visible galaxies. Some of these dark matter concentrations may represent dark galaxies within the cluster environment. Weak gravitational lensing produces more subtle distortions that can only be detected statistically by averaging over many background sources. This technique is used to map the large-scale distribution of dark matter in the universe, revealing the cosmic web of filaments and voids that structures the cosmos. Weak lensing surveys have the potential to detect dark galaxies as localized mass concentrations that produce coherent distortions in background galaxy shapes. Microlensing occurs when a compact object passes in front of a distant star, causing a temporary brightening as the gravitational lens focuses the star's light. This technique has been used to search for dark compact objects in the halos of galaxies, including potential primordial black holes that might contribute to dark matter. While microlensing is not directly applicable to finding extended dark galaxies, it provides complementary information about the nature of dark matter. The interpretation of gravitational lensing signals requires careful modelling and can be subject to degeneracies between different mass distributions. A dark galaxy might produce a lensing signal similar to that of a concentration of dark matter within a larger structure, making it difficult to identify individual dark galaxies through lensing alone. Combining lensing observations with other methods, such as radio detection of hydrogen, provides more robust identifications. Future gravitational lensing surveys will dramatically improve our ability to detect dark matter structures. The Vera C. Rubin Observatory will measure the shapes of billions of galaxies, enabling weak lensing analyses of unprecedented precision. The Euclid space mission, launched by the European Space Agency, is specifically designed for weak lensing cosmology and will map dark matter across large volumes of the universe. These surveys may reveal populations of dark galaxies that have escaped detection through other methods, dynamical methods, inferring mass from motion. Even when dark galaxies cannot be directly detected, their presence can sometimes be inferred from the motions of visible objects in their vicinity. Gravitational interactions leave signatures in the velocities and positions of stars and gas, allowing astronomers to deduce the presence of unseen mass. The rotation curves of spiral galaxies provided some of the earliest evidence for dark matter and continue to be valuable probes of mass distribution. When a visible galaxy shows perturbations in its rotation curve or asymmetries in its gas distribution, these features may indicate the gravitational influence of a nearby dark companion. Several dark galaxy candidates have been identified through their effects on neighbouring visible galaxies. Stellar streams, the elongated structures formed when dwarf galaxies or globular clusters are tidally disrupted by larger galaxies, are sensitive probes of the gravitational potential through which they move. Gaps and density variations in stellar streams can be produced by encounters with dark matter subhalos, including potential dark galaxies. Studies of stellar streams around the Milky Way have revealed evidence for numerous dark subhalos that may represent the predicted population of dark satellites. The dynamics of satellite galaxies around larger hosts also constrain the distribution of dark matter. The velocities and orbital properties of satellites depend on the total mass of the host system, including any dark matter halo and associated dark satellites. Statistical analyses of satellite populations can reveal the presence of dark companions even when individual dark galaxies cannot be identified. Binary galaxy systems provide another dynamical probe. When two galaxies orbit each other, their relative velocities depend on their combined mass. If one member of the pair is a dark galaxy, the visible galaxy will appear to be orbiting an invisible companion. Several candidate dark galaxies have been identified through their gravitational effects on visible binary partners. The challenge with dynamical methods is that they typically provide indirect evidence for dark mass, rather than direct detection of individual dark galaxies. The inferred dark mass might be distributed in various ways, and distinguishing between a discrete dark galaxy and a more diffuse dark matter distribution can be difficult. Combining dynamical evidence with other detection methods provides the most convincing identifications. Absorption line studies, shadows in the light. When light from a distant quasar or galaxy passes through intervening gas, atoms in that gas absorb photons at specific wavelengths, producing absorption lines in the observed spectrum. These absorption lines reveal the presence of gas along the line of sight, even when that gas is not associated with any visible galaxy. Some absorption systems may arise in dark galaxies, providing an indirect method for detecting these objects. Damped Lyman alpha absorbers are particularly interesting in this context. These systems produce strong absorption in the Lyman alpha line of hydrogen, indicating large column densities of neutral hydrogen gas. Many damped Lyman alpha absorbers are associated with visible galaxies, but some have no detected optical counterpart despite deep imaging. These may represent dark galaxies, massive reservoirs of hydrogen that have never formed significant stellar populations. The properties of absorption systems can constrain the nature of the absorbing gas and its host structure. The velocity width of absorption lines indicates the mass of the gravitational potential well, while the chemical abundances revealed by metal absorption lines provide information about the star formation history. Absorption systems associated with dark galaxies would be expected to show low metallicities, reflecting the absence of stellar nucleosynthesis. Follow-up observations of absorbers without optical counterparts have revealed a diverse population. Some turn out to be associated with faint galaxies that were missed in initial imaging. Others appear to be genuinely starless, representing either dark galaxies or gas in the intergalactic medium. Distinguishing between these possibilities requires deep observations across multiple wavelengths. The statistical properties of absorption systems provide constraints on the overall population of gas-rich objects in the universe. If dark galaxies are common, they should contribute significantly to the cross-section for absorption, producing more absorbers than would be expected from visible galaxies alone. Comparisons between observed absorber statistics and predictions from simulations can constrain the abundance of dark galaxies, even when individual objects cannot be identified. Multi-wavelength approaches combining perspectives. The most robust identifications of dark galaxies come from combining multiple detection methods, each providing complementary information about the object's properties. A candidate identified through radio observations of hydrogen can be confirmed through deep optical imaging that rules out a stellar counterpart. Dynamical evidence from the kinematics of the gas can constrain the dark matter content, and gravitational lensing or absorption studies can provide independent checks on the mass distribution. This multi-wavelength approach is becoming increasingly feasible as astronomical surveys expand their coverage across the electromagnetic spectrum. Large-scale surveys in radio, optical, infrared, and X-ray wavelengths are generating catalogues that can be cross-matched to identify objects with unusual properties. Machine learning techniques are being developed to sift through these massive datasets and flag potential dark galaxy candidates for follow-up observation. The coordination of observations across different facilities and wavelengths requires careful planning and collaboration among research teams. International collaborations have become the norm in dark galaxy research, with astronomers pooling resources and expertise to tackle the challenging observations required. The global nature of modern astronomy, with major facilities distributed across multiple continents and in space, enables round-the-clock monitoring and rapid follow-up of interesting targets. As detection methods continue to improve, our census of dark galaxies will become more complete. Objects that are currently beyond our detection limits will be revealed by next-generation facilities. The boundary between visible and invisible will shift, incorporating ever fainter and more diffuse objects into our catalogues. The story of dark galaxy detection is thus an ongoing one, with each technological advance opening new windows onto the hidden universe. Future facilities and prospects. The coming decades will bring transformative new facilities for studying dark galaxies. The square-kilometre array, when completed, will be sensitive enough to detect hydrogen in galaxies at cosmological distances, potentially revealing the evolution of dark galaxies across cosmic time. Its unprecedented resolution will map the gas distributions in nearby dark galaxy candidates with exquisite detail. The Vera C. Rubin Observatory will conduct the legacy survey of space and time, imaging the entire southern sky repeatedly over 10 years. This survey will reach surface brightness levels that will reveal vast numbers of ultra-diffuse and low-surface brightness galaxies. The time domain aspect of the survey will also enable detection of transient phenomena in dark galaxies, such as supernovae that might occasionally occur even in star-poor systems. The James Webb Space Telescope is already revolutionizing our view of faint galaxies, and its observations of dark galaxy candidates will continue for years to come. Its infrared sensitivity is ideal for detecting the old stellar populations that dominate most dark galaxies, while its spectroscopic capabilities enable detailed studies of stellar chemistry and kinematics. Extremely large ground-based telescopes, including the 30-metre telescope, the Giant Magellan Telescope, and the European Extremely Large Telescope, will provide order-of-magnitude improvements in sensitivity and resolution. These facilities will enable spectroscopic studies of individual stars in nearby dark galaxies, revealing their formation histories and chemical evolution in unprecedented detail. Space-based gravitational wave observatories, such as the planned Laser Interferometer Space Antenna, may provide entirely new methods for detecting dark matter structures. Gravitational waves passing through concentrations of dark matter experience subtle effects that could, in principle, reveal the presence of dark galaxies along the line of sight. While this application remains speculative, it illustrates the potential for unexpected discoveries as new observational windows open. The future of dark galaxy research is bright, even as its subject matter remains dim. Each new facility and technique brings the promise of discoveries that will reshape our understanding of these enigmatic objects. The invisible universe is slowly coming into view, revealing a cosmos far richer and more complex than what meets the eye. Understanding how dark galaxies form is one of the central challenges in modern astrophysics. These objects represent failures of the normal galaxy formation process, cases where the usual progression from dark matter halo to gas accumulation to star formation was interrupted or never began. Unraveling the causes of these failures provides insights into the physics of galaxy formation more broadly and into the nature of dark matter itself. The standard picture of galaxy formation. To understand how dark galaxies form, we must first review the standard picture of how normal galaxies come into being. This process begins in the early universe, shortly after the Big Bang, when tiny fluctuations in the density of matter provided the seeds for all future structure. In the standard cosmological model, dark matter dominated the early universe and began to collapse under its own gravity before ordinary matter could do the same. The small density enhancements present in the primordial plasma grew over time, with regions of slightly higher density attracting more matter and becoming denser still. This process of gravitational instability led to the formation of dark matter halos, roughly spherical concentrations of dark matter bound together by gravity. Ordinary matter, consisting primarily of hydrogen and helium gas, initially could not collapse because it was coupled to the intense radiation field that filled the early universe. The pressure of this radiation prevented the gas from falling into the dark matter potential wells. Only after the universe cooled sufficiently for atoms to form, an epoch known as recombination occurring about 380,000 years after the Big Bang, could ordinary matter begin to fall into dark matter halos. As gas fell into dark matter halos, it was heated by compression and by shocks as infalling streams collided. This hot gas could not immediately form stars because thermal pressure supported it against further collapse. For star formation to proceed, the gas needed to cool, radiating away its thermal energy and allowing it to condense into denser structures. The cooling of gas depends on its temperature, density, and chemical composition. At high temperatures, gas cools primarily through the emission of X-rays from highly ionized atoms. At lower temperatures, cooling proceeds through emission lines from partially ionized species and through molecular transitions. The efficiency of cooling determines how quickly gas can condense and ultimately how much star formation occurs. In halos where cooling is efficient, gas settles into a rotating disk at the center of the halo, supported against further collapse by angular momentum. Within this disk, regions of particularly high density become gravitationally unstable and collapse to form molecular clouds, the birthplaces of stars. Star formation proceeds within these clouds, converting gas into stars over timescales of millions to billions of years. The stars that form inject energy back into their surroundings through radiation, stellar winds, and eventually supernova explosions. This feedback can heat the surrounding gas, drive outflows, and regulate the rate of subsequent star formation. The interplay between gas cooling, star formation, and feedback determines the final properties of the galaxy, including its stellar mass, gas content, and morphology. This standard picture successfully explains the properties of most observed galaxies, but it also predicts that some dark matter halos should fail to form significant stellar populations. Dark galaxies arise when one or more steps in this process go wrong, preventing the normal progression from dark matter halo to luminous galaxy. Suppression by reionization. One of the most important mechanisms for creating dark galaxies operates in the early universe during the epoch of reionization. This period, occurring roughly 100 million to 1 billion years after the Big Bang, saw the first stars and galaxies flood the universe with ultraviolet radiation, ionizing the neutral hydrogen that filled intergalactic space. The ultraviolet radiation produced during reionization had profound effects on small dark matter halos. Gas in these halos was heated by the radiation, raising its temperature and pressure. In halos below a certain mass threshold, the heated gas could no longer be gravitationally confined and escaped into intergalactic space. This process, known as photoevaporation, stripped small halos of their baryonic matter and prevented them from ever forming stars. The mass threshold below which halos are affected by reionization depends on the intensity and spectrum of the ionizing radiation, as well as the timing of reionization in different regions of the universe. Detailed calculations suggest that halos with masses below about 10 billion solar masses would have been significantly affected, with the smallest halos losing essentially all of their gas. Halos that were stripped of gas during reionization would remain dark throughout cosmic history, never accumulating enough baryonic matter to form stars. These objects would contribute to the population of dark satellites predicted to surround large galaxies like the Milky Way. Their existence is one proposed solution to the missing satellite problem, explaining why we observe fewer satellite galaxies than simulations predict. The timing of reionization relative to halo formation is crucial. Halos that formed and accumulated gas before reionization occurred might have been able to retain some of that gas, especially if they had already begun forming stars. The first stars in these systems would have provided a local source of ionizing radiation, but they also would have enriched the gas with heavy elements that enhance cooling efficiency. The outcome for any individual halo depended on a complex interplay of factors. Observations of the faintest dwarf galaxies in the local group provide evidence for reionization suppression. These objects have old stellar populations with ages consistent with star formation that occurred before or during reionization, followed by a cessation of star formation that may have been caused by gas loss. The properties of these ancient dwarfs constrain models of reionization and its effects on galaxy formation. Feedback-driven quenching, even in halos massive enough to retain gas through reionization, internal feedback processes can prevent or truncate star formation. The energy released by stars and supernovae can heat gas, drive outflows, and ultimately quench star formation, potentially creating dark or nearly dark galaxies. Supernova feedback is particularly effective in low-mass halos where the gravitational binding energy is modest. A single supernova releases about 10 to the power of 51 ergs of energy, enough to unbind the gas in a small dwarf galaxy if that energy couples efficiently to the interstellar medium. In practice, much of the supernova energy is radiated away, but even a fraction is sufficient to drive significant outflows. The efficiency of supernova feedback depends on the clustering of supernova in space and time. When multiple massive stars form in proximity and explode within a short interval, their combined energy can create superbubbles that break out of the galactic disk and drive large-scale outflows. This clustered feedback is more effective at removing gas than isolated supernovae would be. In the most extreme cases, a single burst of star formation might be sufficient to expel all remaining gas from a low-mass halo, permanently ending star formation. The result would be a dark galaxy containing only the stellar remnants of that initial burst, a fossil of truncated galaxy formation. Some ultra-faint dwarf galaxies may represent such systems, their tiny stellar populations reflecting a brief episode of star formation followed by complete gas loss. Feedback from active galactic nuclei provides another mechanism for quenching star formation, particularly in more massive systems. When matter accretes onto a supermassive black hole at the center of a galaxy, it can release enormous amounts of energy in the form of radiation and jets. This energy can heat the surrounding gas to temperatures where cooling is inefficient, preventing further star formation. Active galactic nucleus feedback is thought to be responsible for quenching star formation in the most massive galaxies, explaining why giant elliptical galaxies contain predominantly old stellar populations. In some scenarios, this feedback might also operate in lower mass systems that happen to form central black holes early in their histories. A dark matter halo that formed a black hole before significant star formation occurred might have had its gas heated and expelled, remaining dark thereafter. The interplay between stellar feedback and black hole feedback creates a complex landscape of possible outcomes. Different halos with different masses, formation histories, and environments experience different feedback histories and arrive at different final states. The diversity of dark and dim galaxies we observe reflects this diversity of formation pathways. High angular momentum scenarios. Another mechanism for producing dark galaxies involves the angular momentum of the gas that falls into dark matter halos. gas with high angular momentum settles into extended, low-density configurations that may be unfavorable for star formation. Angular momentum is acquired through tidal torques, gravitational interactions between a forming halo and its neighbours that impart rotational motion. The amount of angular momentum a halo acquires depends on its environment, with halos in dense regions experiencing stronger torques than those in isolation. There is significant scatter in the angular momentum of halos at any given mass, leading to a range of possible disk configurations. Gas with high angular momentum settles into disks with large radii and low surface densities. In such disks, the gas may never reach the densities required for gravitational instability and molecular cloud formation. Star formation would be suppressed, producing a gas-rich but star-poor system, essentially a dark galaxy with an extended hydrogen disk. The stability of gas disks against star formation depends on the balance between gravity, which promotes collapse, and pressure and rotation, which oppose it. This balance is characterized by the Toomre parameter, a dimensionless quantity that determines whether a disk is stable or unstable to fragmentation. Disks with high angular momentum and low surface density have high Toomre parameters and are stable against star formation. Some observed dark galaxy candidates show properties consistent with high angular momentum formation. They contain substantial hydrogen gas spread across large areas, with rotation velocities indicating significant angular momentum. The gas appears stable against collapse, explaining the absence of ongoing star formation despite the available raw material. High angular momentum scenarios can operate in isolation without requiring external influences like reionization or environmental effects. This makes them attractive explanations for dark galaxies found in the field, far from any large galaxy or cluster. However, distinguishing high angular momentum systems from other types of dark galaxies requires detailed observations of gas kinematics, which are challenging for faint, extended objects. Environmental transformation. The environment in which a galaxy resides can profoundly influence its evolution, and environmental processes represent important pathways for creating dark galaxies. Galaxies in dense environments, such as groups and clusters, experience interactions that can remove gas, strip stars, and transform their properties. Ram pressure stripping occurs when a galaxy moves through a hot, diffuse medium, such as the intracluster gas that pervades galaxy clusters. The pressure of this medium on the galaxy's interstellar gas can exceed the gravitational restoring force, stripping gas from the galaxy. Complete stripping removes the fuel for star formation, quenching the galaxy and potentially transforming it into a dark or dim system. The effectiveness of Ram pressure stripping depends on the density of the surrounding medium, the velocity of the galaxy through that medium, and the gravitational binding of the galaxy's gas. Low-mass galaxies with shallow gravitational potentials are most susceptible to stripping, while massive galaxies can retain their gas even in dense cluster environments. Tidal interactions between galaxies can also remove gas and stars, transforming normal galaxies into dark remnants. When two galaxies pass close to each other, gravitational tides can strip material from their outer regions, creating tidal streams and debris. In extreme cases, the entire stellar population of a small galaxy might be stripped away, leaving behind only the dark matter halo. Tidal heating is a related process in which gravitational interactions inject energy into a galaxy's stellar orbits, puffing up the stellar distribution and lowering the surface brightness. A compact dwarf galaxy that experiences repeated tidal encounters might be transformed into an ultra-diffuse system, with stars spread across a much larger volume than they originally occupied. The transformation of normal galaxies into dark or dim systems through environmental processes implies that some dark galaxies were not always dark. They may have had normal stellar populations in the past before environmental effects removed or dispersed their stars and gas. The stellar remnants of these transformations, if any survive, would provide clues to the galaxy's history. Evidence for environmental transformation comes from the spatial distribution of dark and dim galaxies within clusters. These objects are often found preferentially in regions where environmental effects would be strongest, such as near the cluster center or along infalling filaments. The correlation between location and properties supports the role of environment in shaping dark galaxy populations. Failed massive galaxy scenarios. Some of the most intriguing dark galaxies are massive systems that appear to have the dark matter halos of major galaxies, but only a tiny fraction of the expected stellar mass. These objects challenge our understanding because their halos should have been capable of forming substantial stellar populations. One explanation for failed massive galaxies invokes early and efficient feedback that expelled gas before significant star formation could occur. If a massive halo formed a supermassive black hole very early in its history, the energy released by accretion onto that black hole might have heated and ejected the gas, preventing star formation. The result would be a massive dark matter halo with only a small stellar population formed during the brief interval before feedback became effective. Another possibility involves unusual formation histories. A massive halo might have assembled through mergers of smaller halos that were themselves dark, having lost their gas to rionization or feedback. The merged system would inherit the dark nature of its progenitors, remaining gas-poor and star-poor despite its large total mass. The environment during halo formation might also play a role. A halo forming in a region that had been swept clean of gas by previous generations of galaxies would have no raw material for star formation, regardless of its mass. Such regions might exist in the wakes of powerful galactic outflows, or in areas where early galaxy formation was particularly vigorous. Failed massive galaxies are rare, but their existence provides important constraints on galaxy formation models. Any successful theory must explain not only the typical outcome, in which massive halos become massive galaxies, but also the exceptional cases where this process fails. The properties of objects like Dragonfly 44 test the limits of our understanding. Multiple pathways and diversity. The diversity of dark galaxies we observe suggests that no single formation mechanism dominates. Different dark galaxies likely formed through different pathways, with the relative importance of various mechanisms depending on mass, environment, and cosmic epoch. Low-mass dark galaxies in the halos of larger systems may have formed primarily through rionization suppression, losing their gas in the early universe before star formation could begin. Intermediate mass dark galaxies might have experienced feedback-driven quenching, forming some stars before supernova expelled their remaining gas. Massive dark galaxies in clusters may have been transformed from normal galaxies through environmental processes like ram pressure stripping and tidal interactions. The formation pathways of dark galaxies connect to broader questions about galaxy formation and evolution. Understanding why some halos remain dark, while others form bright galaxies, illuminates the physics that governs the conversion of gas into stars. The boundary between dark and luminous is not sharp but represents a continuum of outcomes determined by the complex interplay of many factors. As simulations become more sophisticated and observations probe fainter objects, our understanding of dark galaxy formation will continue to evolve. The current picture, with its multiple pathways and diverse outcomes, is likely to be refined and extended as new data become available. The story of how dark galaxies form is still being written, with each new discovery adding another chapter to our understanding. Galaxies do not exist in isolation. They are embedded in a cosmic web of dark matter and gas, surrounded by neighbours near and far, and subject to influences that extend across millions of light years. The environment in which a galaxy resides profoundly shapes its evolution, and understanding these environmental effects is crucial for understanding dark galaxies. The cosmic web. The large-scale structure of the universe resembles a vast, three-dimensional web, with galaxies distributed along filaments and walls that surround enormous voids where almost nothing exists. This cosmic web emerged from the gravitational amplification of tiny density fluctuations in the early universe, with matter flowing from underdense regions into overdense ones over billions of years. The nodes of the cosmic web, where multiple filaments intersect, are the sites of galaxy clusters, the largest gravitationally bound structures in the universe. These clusters contain hundreds to thousands of galaxies, embedded in a common halo of dark matter and bathed in hot X-ray emitting gas. The environment within clusters is extreme, with high galaxy densities, frequent interactions, and a pervasive hot medium that affects any galaxy passing through it. Filaments connect clusters to each other, serving as highways along which matter flows toward the densest regions. Galaxies within filaments experience intermediate environmental effects, less extreme than in clusters, but more significant than in the field. The gas within filaments is warm and diffuse, capable of affecting galaxy evolution through accretion and stripping processes. Voids are the emptiest regions of the universe, vast bubbles where the density of matter is far below the cosmic average. Galaxies in voids are rare and widely separated, experiencing minimal environmental influences. Any dark galaxies in voids would have evolved in relative isolation, their properties determined primarily by internal processes rather than external interactions. The position of a galaxy within the cosmic web influences its likelihood of becoming or remaining dark. Galaxies in dense environments face numerous processes that can remove gas and quench star formation, while galaxies in sparse environments may lack the interactions that trigger star formation in the first place. The relationship between environment and dark galaxy properties provides clues to the mechanisms that create these objects. Cluster environments. Galaxy clusters are particularly important environments for understanding dark galaxies. The extreme conditions within clusters, including high galaxy densities, hot intracluster gas, and strong gravitational tides, create a hostile environment for normal galaxy evolution. Many of the processes that can transform galaxies into dark systems operate most efficiently in clusters. Ram pressure stripping is especially effective in clusters because of the high density and temperature of the intracluster medium. A galaxy falling into a cluster for the first time can have its gas stripped on a single passage through the cluster center, a process that takes only a few 100 million years. The stripped gas joins the intracluster medium, while the galaxy is left devoid of fuel for star formation. The efficiency of ram pressure stripping varies with the mass and trajectory of the infalling galaxy. Low-mass galaxies with shallow gravitational potentials lose their gas most easily, while massive galaxies can retain at least some gas even after passing through the cluster center. Galaxies on radial orbits that plunge deep into the cluster experience stronger stripping than those on more circular orbits that remain in the outskirts. Observations of galaxies in clusters reveal the effects of ram pressure stripping in action. Some cluster galaxies show spectacular tails of stripped gas extending behind them as they move through the intracluster medium. Others show truncated gas disks, with star formation continuing in the centre, but absent in the outer regions, where gas has been removed. The progression from normal spiral to gas-poor lenticular to completely quenched elliptical can be traced through cluster galaxy populations. Tidal effects are also enhanced in clusters because of the high density of galaxies and the strong gravitational field of the cluster as a whole. Galaxies passing close to each other experience tidal forces that can strip stars and gas from their outer regions. Repeated encounters gradually erode galaxies, reducing their mass and potentially transforming them into ultra-diffuse or dark systems. The phenomenon of galaxy harassment describes the cumulative effect of many high-speed encounters in cluster environments. Unlike major mergers, which involve slow, close passages between comparable galaxies, harassment involves rapid, distant encounters that individually produce small effects, but collectively transform galaxy properties over time. Harassment can heat stellar orbits, strip outer material, and trigger bursts of star formation that consume remaining gas. The infall history of galaxies into clusters determines their exposure to these environmental processes. Galaxies that fell into clusters early have had more time to be affected and are generally more transformed than recent arrivals. The spatial distribution of galaxy properties within clusters, with more evolved galaxies toward the centre and less evolved galaxies in the outskirts, reflects this infall history. Ultra-diffuse galaxies are particularly abundant in clusters, suggesting that cluster environments play a role in their formation or survival. Some ultra-diffuse galaxies may have been created through tidal heating and stripping of normal dwarf galaxies. Others may have formed as ultra-diffuse systems elsewhere and subsequently fallen into clusters. The relative importance of these pathways is still debated. The survival of ultra-diffuse galaxies in cluster environments is itself a puzzle. These diffuse, loosely bound systems might be expected to be easily disrupted by tidal forces, yet they persist in significant numbers even near cluster centres. Their survival suggests that they are embedded in substantial dark matter halos that provide gravitational protection, consistent with the high mass-to-light ratios inferred for some ultra-diffuse galaxies. Group environments, galaxy groups containing a few to a few dozen galaxies, represent intermediate environments between isolated field galaxies and dense clusters. The environmental effects in groups are generally milder than in clusters, but can still significantly influence galaxy evolution over cosmic time. The Milky Way resides in a small galaxy group called the Local Group, which also includes the Andromeda Galaxy, the Triangulum Galaxy, and several dozen smaller companions. Studies of local group galaxies provide detailed insights into environmental effects at the group scale, including the influence of the Milky Way and Andromeda on their satellite populations. Many of the faintest known galaxies are satellites of the Milky Way or Andromeda, their properties shaped by billions of years of interaction with their massive hosts. These ultra-faint dwarfs may have lost gas through tidal stripping or ram pressure from the hot gas halos that surround large galaxies. Some may have had their star formation quenched by rionization, with subsequent environmental effects preventing any recovery. The distinction between satellites that formed in place around their hosts and those that were accreted from the field has implications for understanding dark galaxy populations. Satellites that formed early in the host's halo would have experienced the full history of environmental effects, while recent arrivals would have spent most of their lives in isolation. The properties of dark satellites might differ depending on their accretion history. Pre-processing in groups before cluster infall represents another important environmental pathway. Many galaxies that currently reside in clusters were previously members of groups that subsequently merged with the cluster. Environmental effects operating in these groups, including tidal interactions and gas stripping, would have begun transforming galaxies before they ever entered the cluster environment. The importance of pre-processing is evident in observations of infalling groups at the outskirts of clusters. Galaxies in these groups often show signs of environmental transformation, including reduced gas content and suppressed star formation, even though they have not yet experienced the extreme conditions of the cluster core. This pre-processing can prime galaxies for rapid transformation once they enter the cluster. Field environments. Galaxies in the field, far from any group or cluster, experience minimal environmental influences. Their evolution is determined primarily by internal processes, including gas accretion from the intergalactic medium, star formation and feedback, and secular dynamical evolution. Dark galaxies in the field provide insights into formation mechanisms that operate independently of environment. The existence of dark galaxies in the field demonstrates that environmental processes are not required to suppress star formation. Some dark matter halos apparently fail to form stars even in the absence of external influences. Understanding why requires examining the internal properties of these systems, including their mass, angular momentum, gas content, and formation history. Field dark galaxies may represent halos that were affected by reionization in the early universe, losing their gas before environmental effects could play a role. Alternatively, they may be high angular momentum systems where gas settled into stable configurations that resist star formation, or they may have experienced early feedback that expelled their gas, leaving them dark despite their isolation. The properties of field dark galaxies provide important constraints on formation mechanisms. If these objects show evidence for old stellar populations, even very sparse ones, this would suggest that some star formation occurred before quenching. If they are completely devoid of stars, this would point toward mechanisms that prevented star formation entirely, such as reionization suppression or extreme angular momentum. Comparisons between dark galaxies in different environments can reveal which formation mechanisms dominate in each setting. If cluster dark galaxies have different properties than field dark galaxies, this would suggest that different processes are responsible. Conversely, if dark galaxies show similar properties regardless of environment, this might indicate a common formation pathway that operates independently of external influences. The isolation of field dark galaxies also makes them valuable laboratories for studying dark matter. Without the complications introduced by environmental effects, the dynamics of field dark galaxies should be determined primarily by their dark matter halos. Measurements of gas kinematics in these systems can probe the distribution of dark matter with minimal contamination from baryonic processes. Dark matter halos extend well beyond the luminous boundaries of the galaxies they surround, and studies show that dark matter and luminous matter are very closely associated in normal galaxies. In dark galaxies, this association breaks down, with dark matter halos existing largely or entirely without luminous counterparts. Understanding this decoupling is central to understanding dark galaxy formation. Void environments, the most extreme field environments, are cosmic voids, the vast underdense regions that occupy most of the volume of the universe. Galaxies in voids are rare and widely separated, experiencing essentially no environmental influences beyond the general expansion of the universe. Void galaxies tend to be bluer and more actively star-forming than galaxies in denser environments, suggesting that the absence of environmental quenching allows star formation to continue unimpeded. However, voids may also contain dark galaxies, halos that fail to form stars despite their isolation. The properties of void dark galaxies would be particularly informative because they would reflect formation mechanisms operating in the most pristine conditions. Any dark galaxy in a void must have become dark through internal processes or early universe effects like rionization, since environmental transformation is essentially impossible in these empty regions. Searches for dark galaxies in voids face significant challenges. The low density of objects in voids means that large volumes must be surveyed to find significant numbers of candidates. The distances to void regions are typically large, making faint objects difficult to detect, and the absence of nearby reference objects complicates distance measurements and other characterizations. Despite these challenges, void environments represent an important frontier for dark galaxy research. The discovery of dark galaxies in voids would demonstrate conclusively that environmental processes are not required for their formation. The absence of dark galaxies in voids, conversely, might suggest that environmental transformation is the dominant formation pathway. Environmental dependence of dark galaxy properties. The relationship between environment and dark galaxy properties provides clues to formation mechanisms. By comparing dark galaxies across different environments, astronomers can identify which properties are environmentally dependent and which are intrinsic to the objects themselves. The abundance of dark galaxies varies with environment, with higher fractions found in dense regions, like clusters, compared to the field. This environmental dependence suggests that cluster-specific processes contribute to dark galaxy formation, though it does not rule out additional contributions from environment-independent mechanisms. The morphologies of dark galaxies may also depend on environment. Ultra-diffuse galaxies in clusters tend to be rounder and more featureless than those in the field, possibly reflecting tidal heating that has erased any original disk structure. Field ultra-diffuse galaxies sometimes show more irregular morphologies, suggesting different formation or evolution pathways. The stellar populations of dark galaxies provide another environmental diagnostic. Cluster dark galaxies tend to have uniformly old stellar populations, consistent with early quenching, followed by passive evolution. Field dark galaxies show more diversity, with some having old populations similar to cluster objects, and others showing evidence for more extended star formation histories. The gas content of dark galaxies varies dramatically with environment. Cluster dark galaxies are typically gas-poor, having lost their hydrogen to ram pressure stripping or other environmental processes. Field dark galaxies are more likely to retain gas, with some containing substantial hydrogen reservoirs despite their low stellar content. These environmental trends support a picture in which multiple formation pathways contribute to the dark galaxy population. Cluster dark galaxies may form primarily through environmental transformation of normal galaxies, while field dark galaxies may form through internal processes or early universe effects. The relative importance of different pathways varies with environment, producing the observed trends in dark galaxy properties. The influence of large-scale structure. Beyond the immediate environment of groups and clusters, the large-scale structure of the universe may influence dark galaxy formation and evolution. The cosmic web channel's matter flows determines the availability of gas for accretion and creates the conditions under which galaxies form and evolve. Galaxies forming in filaments may have different properties than those forming in nodes or voids. The gas in filaments is warm and flowing, potentially providing a continuous supply of fuel for star formation. Galaxies in filaments might therefore be less likely to become dark than those in other environments, though this prediction has not been thoroughly tested. The orientation of galaxies relative to filaments may also matter. Galaxies aligned with filaments might accrete gas more efficiently than those oriented perpendicular to the flow. This could create systematic differences in gas content and star formation that influence the likelihood of becoming dark. The history of large-scale structure growth affects the environments that galaxies experience over cosmic time. A galaxy that formed in a void might later find itself in a filament or cluster as structure evolves. The cumulative environmental history, rather than the current environment alone, determines the galaxy's properties. Simulations of cosmic structure formation can track the environmental histories of individual halos, revealing how their properties depend on the sequence of environments they have experienced. These simulations predict that dark galaxies should be more common in certain environments and should have characteristic properties that reflect their formation pathways. Comparing these predictions to observations tests, our understanding of both dark galaxies and large-scale structure. The connection between dark galaxies and large-scale structure extends to cosmological questions about the nature of dark matter and the growth of structure. Dark matter halos play a key role in current models of galaxy formation and evolution, providing the gravitational scaffolding upon which visible structures are built. Dark galaxies represent halos where this scaffolding exists, but the visible structure failed to develop, offering unique insights into the relationship between dark and luminous matter. The study of dark galaxies extends beyond the objects themselves to address fundamental questions about the nature of the universe. These enigmatic structures provide unique probes of dark matter, test models of galaxy formation, and illuminate the processes that shape the cosmos from its earliest moments to the present day. Constraining dark matter properties. Dark galaxies offer valuable opportunities to study dark matter in systems where baryonic matter plays a minimal role. In normal galaxies, the gravitational effects of stars and gas complicate efforts to measure dark matter distributions. In dark galaxies, dark matter dominates so completely that its properties can be probed more directly. The density profiles of dark matter halos are predicted by theoretical models to follow specific functional forms. The most widely used is the Navarro-Frank-White profile, which describes how dark matter density varies with distance from the halo center. This profile predicts a central cusp where density rises steeply toward the center, a feature that has been difficult to confirm observationally in normal galaxies. Dark galaxies provide cleaner tests of halo density profiles because their dynamics are dominated by dark matter. By measuring the velocities of any gas or stars present, astronomers can map the gravitational potential and infer the dark matter distribution. Results from dark galaxy studies have been mixed, with some objects consistent with cuspy profiles and others suggesting flatter central cores. The core cusp problem, the apparent discrepancy between predicted cusps and observed cores, has important implications for dark matter physics. If dark matter halos truly have cores rather than cusps, this might indicate that dark matter particles interact with each other in ways not captured by the simplest models. Alternatively, baryonic processes might modify halo structure even in dark galaxies, though this seems less likely given their low baryon content. The substructure of dark matter halos provides another test of dark matter models. Cold dark matter simulations predict that large halos should contain numerous smaller subhalos, remnants of the smaller structures that merge to form the larger system. The abundance and properties of these subhalos depend on the nature of dark matter, with different candidates predicting different substructure populations. Dark galaxies may themselves be subhalos within larger systems, representing the predicted population of dark satellites around galaxies like the Milky Way. The number of dark satellites, their mass distribution, and their spatial arrangement all constrain dark matter models. Searches for dark satellites through gravitational effects on stellar streams and other tracers are ongoing. The minimum mass of dark matter halos that can form is set by the properties of dark matter particles. If dark matter is warm rather than cold, meaning the particles have significant thermal velocities, small-scale structure is suppressed and the minimum halo mass is larger. Computational astrophysicists have calculated the mass below which halos fail to form stars, using analytic predictions from galaxy formation theory and cosmological simulations. The observed population of dark galaxies and ultra-faint dwarfs constrains these calculations, and by extension, the properties of dark matter. Alternative theories of gravity propose to explain galactic dynamics without invoking dark matter, face challenges from dark galaxy observations. These theories, including modified Newtonian dynamics and its relativistic extensions, predict that all galaxies should show similar deviations from Newtonian expectations based on their visible matter content. The existence of galaxies with vastly different dark matter fractions, from dark matter-dominated systems like Dragonfly 44 to dark matter-deficient systems like NGC 1052 DF2, is more naturally explained if dark matter is a real substance present in varying amounts. Testing galaxy formation models. Dark galaxies provide stringent tests of galaxy formation models because they represent the failures of the standard process. Any successful model must explain not only why most halos form luminous galaxies, but also why some do not. The efficiency of star formation as a function of halo mass is a key prediction of galaxy formation models. At low masses, star formation is suppressed by reionization and feedback, while at high masses it is suppressed by active galactic nucleus feedback. The result is a characteristic relationship between halo mass and stellar mass, with the highest efficiency at intermediate masses. Dark galaxies probe the low-efficiency tails of this relationship, representing halos where star formation was even less efficient than typical. Understanding why these halos fail to form stars tests our models of the physical processes that regulate star formation, including gas cooling, feedback, and angular momentum. The abundance of dark galaxies as a function of mass and environment is another key prediction. Models that include reionization suppression predict many dark satellites around large galaxies, while models with efficient feedback predict dark galaxies across a range of masses. Comparing predicted and observed abundances tests these models and constrains the parameters that govern star formation efficiency. The properties of individual dark galaxies, including their sizes, gas contents, and stellar populations, provide additional constraints. Models must reproduce not only the existence of dark galaxies, but also their detailed characteristics. Discrepancies between predictions and observations highlight areas where our understanding is incomplete. Cosmological simulations have become increasingly sophisticated in their treatment of baryonic physics, incorporating detailed models of gas cooling, star formation, feedback, and chemical enrichment. These simulations can now produce realistic galaxy populations that match many observed properties. However, the dark galaxy regime remains challenging, with different simulations making different predictions about the abundance and properties of these objects. The comparison between simulations and observations is complicated by selection effects. Simulations can identify all dark matter halos regardless of their luminosity, while observations are limited to objects above certain detection thresholds. Careful modelling of observational selection is required to make fair comparisons, and uncertainties in this modelling contribute to uncertainties in our conclusions. Implications for cosmic evolution. Dark galaxies have implications for our understanding of cosmic evolution, the history of how the universe transformed from a nearly uniform state after the Big Bang to the structured cosmos we observe today. The epoch of reionization, when the first stars and galaxies ionized the intergalactic medium, was a pivotal period in cosmic history. The ultraviolet radiation produced during this epoch affected the formation of subsequent generations of galaxies, suppressing star formation in small halos and shaping the properties of the dwarf galaxy population. Dark galaxies that form during or before reionization carry information about conditions in the early universe. Their stellar populations, if any exist, record the chemical abundances and star formation rates of the first generations of stars. Their dark matter halos preserve information about the primordial density fluctuations from which they formed. The contribution of dark galaxies to the total mass budget of the universe is uncertain but potentially significant. If dark galaxies are numerous, they could represent a substantial fraction of the dark matter in galactic halos, with implications for estimates of the total matter content of the universe. The role of dark galaxies in the cosmic web is another area of interest. These objects may trace the distribution of dark matter in filaments and voids, providing information about large-scale structure that is difficult to obtain from luminous galaxies alone. Mapping the dark galaxy population could reveal the full extent of the cosmic web, including regions where luminous matter is sparse. The evolution of dark galaxies over cosmic time is largely unknown. Some may remain dark indefinitely, never accumulating enough gas to form stars. Others may eventually acquire gas through accretion or mergers, transitioning from dark to luminous. Still others may be destroyed through tidal disruption or mergers with larger systems. Understanding these evolutionary pathways requires observations of dark galaxies at different cosmic epochs, a challenging goal that future facilities may achieve. The Baryon budget. One of the puzzles in cosmology is the fate of the baryons, the ordinary matter that makes up stars, gas, and everything we can see. The total amount of baryonic matter in the universe is well constrained by observations of the cosmic microwave background and by measurements of light element abundances from Big Bang nucleosynthesis. However, when astronomers add up all the baryons they can detect in stars, gas, and other forms, the total falls short of the expected amount. This missing baryon problem has several proposed solutions. Some baryons may reside in a warm, hot intergalactic medium that is difficult to detect. Others may be in the form of cool gas in galactic halos or in the circumgalactic medium surrounding galaxies. And some may be in dark galaxies, reservoirs of gas that have escaped detection because they lack the stellar populations that would make them visible. The gas content of dark galaxies could contribute significantly to the baryon budget if these objects are sufficiently numerous. Hydrogen-rich dark galaxies detected through radio observations represent one component of this population, but there may be additional dark galaxies with gas in forms that are harder to detect, such as molecular hydrogen or ionized gas. Accounting for all the baryons in the universe requires a complete census of matter in all its forms, including the gas in dark galaxies. This census is one of the goals of upcoming surveys with facilities like the Square Kilometre Array, which will detect hydrogen in galaxies across cosmic time and potentially reveal populations of gas-rich dark galaxies that have escaped previous detection. Dark galaxies and the nature of darkness. At a deeper level, dark galaxies prompt us to reflect on the nature of darkness itself in the cosmos. The universe is predominantly dark, with dark matter and dark energy together comprising about 95% of the total content. Luminous matter, the stars and gas that produce the light we see, is a minority component, a thin frosting on a vast dark cake. Dark galaxies embody this cosmic darkness in a particularly striking way. They are structures of galactic scale, comparable in mass to the Milky Way in some cases, yet they produce almost no light. They remind us that the visible universe is not the whole universe, that most of what exists is hidden from our direct view. The study of dark galaxies is thus part of a broader effort to understand the dark universe, to map the distribution of dark matter, to probe the nature of dark energy, and to comprehend the cosmic web of invisible structure that underlies everything we see. Each dark galaxy discovered is a small victory in this effort, a glimpse of the hidden architecture of the cosmos. As you rest and let these ideas settle, consider the profound strangeness of a universe where most of what exists cannot be seen. The stars that fill the night sky, beautiful as they are, represent only a tiny fraction of the matter around us. The galaxies we photograph and study are embedded in vast halos of invisible substance, and scattered throughout the cosmos are entire galaxies that produce almost no light at all, dark giants hiding in plain sight. This is the universe we inhabit, a place of light and shadow, of visibility and invisibility, of the known and the unknown. Dark galaxies are messengers from the hidden majority, reminders that our picture of the cosmos is always incomplete. They invite us to look deeper, to develop new ways of seeing, and to remain humble in the face of cosmic mystery. The study of dark galaxies is a vibrant and rapidly evolving field, with new discoveries and insights emerging regularly. Current research spans a wide range of topics, from detailed studies of individual objects to statistical analyses of populations to theoretical modelling of formation mechanisms. In this section, we survey the current state of the field and look ahead to the discoveries that future facilities and techniques may bring. Ongoing observational programs. Several major observational programs are currently advancing our understanding of dark galaxies. These programs employ a variety of techniques and target different aspects of the dark galaxy phenomenon. Deep imaging surveys continue to discover new ultra-diffuse and low-surface brightness galaxies. The Hyper-Suprime Cam Subaru strategic program has surveyed large areas of the sky to unprecedented depths, revealing thousands of faint galaxies that were previously unknown. Analysis of these data is ongoing, with new ultra-diffuse galaxy candidates being identified and characterized. Radio surveys for neutral hydrogen are expanding our census of gas-rich dark galaxy candidates. The Alfalfa survey has been completed, but its data continue to yield new discoveries as astronomers develop improved analysis techniques. New surveys with upgraded facilities, including the Aperative system on the Westerbork telescope and the Australian Square Kilometre Array Pathfinder, are extending the search to new regions of the sky and new redshift ranges. Spectroscopic follow-up of dark galaxy candidates is providing crucial information about their dynamics and stellar populations. Measuring the velocities of stars or globular clusters in these faint systems is challenging but essential for determining their dark matter content. Programs on large telescopes, including Keck, Gemini, and the Very Large Telescope, are slowly building up samples of dark galaxies with dynamical measurements. Gravitational lensing studies are probing dark matter structure on scales relevant to dark galaxies. Strong lensing analyses of galaxy clusters have revealed dark matter substructure that may include dark galaxy-scale halos. Weak lensing surveys are mapping the distribution of dark matter on larger scales, providing context for understanding where dark galaxies might reside. The James Webb Space Telescope is contributing to dark galaxy research through its unprecedented infrared sensitivity. Observations of nearby ultra-diffuse galaxies are resolving their stellar populations in detail, revealing star formation histories and chemical abundances. Deeper observations are probing the faint outskirts of these systems, searching for extended stellar halos that might indicate past interactions. Theoretical and computational advances. Theoretical understanding of dark galaxies is advancing through a combination of analytic modelling and numerical simulation. These efforts aim to explain the observed properties of dark galaxies and to predict the characteristics of populations that have not yet been detected. Cosmological simulations have reached the resolution and physical fidelity needed to produce realistic dark galaxy populations. Simulations like Illustrise TNG, Eagle, and Fire incorporate detailed treatments of gas physics, star formation, and feedback, allowing them to track the formation and evolution of galaxies across cosmic time. These simulations predict the abundance, properties, and environments of dark galaxies, providing benchmarks for comparison with observations. Idealized simulations focus on specific physical processes relevant to dark galaxy formation. Simulations of ram pressure stripping track how galaxies lose gas as they move through cluster environments. Simulations of tidal interactions explore how encounters between galaxies can transform their properties. Simulations of feedback examine how energy injection from stars and black holes affects gas content and star formation. Analytic models provide complementary insights by distilling complex physics into tractable mathematical frameworks. Models of reionization suppression predict the mass scale below which halos should be dark. Models of angular momentum acquisition predict the spin distribution of halos and the resulting disk properties. Models of feedback predict the relationship between star formation and gas loss. The interplay between theory and observation is driving progress in the field. Theoretical predictions motivate observational searches, while observational discoveries challenge and refine theoretical models. This iterative process is gradually converging on a comprehensive understanding of dark galaxy formation and evolution. Machine learning techniques are increasingly being applied to dark galaxy research. Neural networks can be trained to identify faint, extended objects in imaging data, potentially discovering dark galaxy candidates that would be missed by traditional detection algorithms. Machine learning can also be used to classify objects, distinguishing genuine dark galaxies from contaminants like tidal debris or imaging artifacts. Key open questions. Despite significant progress, many fundamental questions about dark galaxies remain unanswered. These open questions define the frontier of the field and motivate ongoing and future research. What is the true abundance of dark galaxies? Current surveys are limited by sensitivity and sky coverage, and the detected population represents only the tip of the iceberg. The total number of dark galaxies in the universe and their contribution to the cosmic mass budget remains highly uncertain. What are the dominant formation mechanisms for dark galaxies. Multiple pathways have been proposed, including reionization suppression, feedback-driven quenching, high angular momentum, and environmental transformation. The relative importance of these mechanisms and how they vary with mass and environment is not yet established. How do dark galaxies evolve over cosmic time? Do they remain dark indefinitely, or can they acquire gas and begin forming stars? Are they eventually destroyed through mergers or tidal disruption? The evolutionary histories of dark galaxies are largely unknown. What do dark galaxies tell us about dark matter? The properties of dark galaxy halos, including their density profiles, substructure, and minimum mass, constrain dark matter models. Extracting these constraints requires careful observations and modelling, and current results are often ambiguous. How do dark galaxies relate to other low-surface brightness phenomena? The boundaries between dark galaxies, ultra-diffuse galaxies, and normal low-surface brightness galaxies are fuzzy. Understanding the relationships among these populations and whether they form a continuum or distinct classes is an ongoing challenge. Future facilities and prospects. The coming years will bring transformative new facilities that promise to revolutionize dark galaxy research. These facilities will extend our detection capabilities, improve our characterization of known objects, and potentially reveal entirely new populations. The Vera C. Rubin Observatory will conduct the Legacy Survey of Space and Time, the most ambitious optical survey ever attempted. Over 10 years, this survey will image the entire southern sky repeatedly, reaching surface brightness levels that will reveal vast numbers of ultra-diffuse and low-surface brightness galaxies. The survey's combination of depth, area, and time coverage will enable discoveries that are impossible with current facilities. The Square Kilometre Array will be the world's most sensitive radio telescope, capable of detecting neutral hydrogen in galaxies across cosmic time. This facility will conduct blind surveys for hydrogen-rich objects, potentially discovering large populations of gas-rich dark galaxies that have escaped optical detection. The SKA's resolution will also enable detailed mapping of gas distributions in nearby dark galaxy candidates. The Nancy Grace Roman Space Telescope will conduct wide-field infrared surveys that complement ground-based optical observations. Its sensitivity to old stellar populations will be valuable for detecting and characterizing the faint stars in dark galaxies. The Roman telescope will also conduct gravitational lensing surveys that may reveal dark matter substructure on dark galaxy scales. Extremely large ground-based telescopes, including the 30-meter telescope, the Giant Magellan Telescope, and the European Extremely Large Telescope, will provide order-of-magnitude improvements in sensitivity and resolution. These facilities will enable spectroscopic studies of individual stars in nearby dark galaxies, revealing their formation histories and chemical evolution in unprecedented detail. The next generation of gravitational wave observatories may provide entirely new probes of dark matter structure. The Laser Interferometer Space antenna will detect gravitational waves from merging supermassive black holes, and the properties of these waves may be affected by dark matter along the line of sight. While speculative, this possibility illustrates the potential for unexpected discoveries as new observational windows open. The continuing quest. The search for dark galaxies is part of a broader quest to understand the universe in all its complexity. These objects challenge our assumptions, test our theories, and expand our conception of what a galaxy can be. Each new discovery adds to our knowledge and raises new questions, driving the ongoing exploration of the cosmos. The progress made in recent decades has been remarkable. From the first tentative identifications of dark galaxy candidates to the current census of hundreds of ultra-diffuse galaxies, the field has advanced rapidly. Yet we are still in the early stages of understanding these enigmatic objects. The true population of dark galaxies, their formation mechanisms, their evolution, and their implications for cosmology all remain to be fully elucidated. The scientists who study dark galaxies are motivated by curiosity, by the desire to understand the universe as it truly is rather than as it superficially appears. They develop new instruments, devise clever observational strategies, and build sophisticated theoretical models, all in pursuit of objects that do not want to be found. Their work exemplifies the spirit of scientific exploration, the willingness to look beyond the obvious and to seek understanding in the darkness. As you rest and let your thoughts drift, consider that somewhere out there, in the vast reaches of intergalactic space, dark galaxies are waiting to be discovered. Some may be massive structures rivaling the Milky Way, their enormous dark matter halos containing only a scattering of ancient stars. Others may be small and isolated, hydrogen clouds that never ignited the fires of stellar fusion. Still others may be in transition, slowly accumulating gas that will one day collapse into new generations of stars. These objects exist whether we find them or not, their presence shaping the gravitational landscape of the cosmos. But through the efforts of astronomers around the world, using instruments on mountaintops and in space, we are gradually bringing them into view. The invisible is becoming visible, the unknown is becoming known, and our picture of the universe is expanding to encompass realms that were once hidden in darkness. As we approach the end of our journey through the realm of dark galaxies, let us pause to reflect on what we have learned and to appreciate the profound wonder that these objects inspire. We have travelled from the theoretical predictions that first suggested dark galaxies should exist, through the painstaking observations that eventually found them, to the cutting-edge research that continues to reveal their secrets. Along the way, we have encountered some of the most fascinating objects in the universe and grappled with some of the deepest questions in cosmology. The beauty of the unseen. There is a particular beauty in things that cannot be easily seen, a mystery that invites contemplation and rewards patience. Dark galaxies embody this beauty in cosmic form. They are structures of immense scale and significance, yet they hide themselves from casual observation, revealing their presence only to those who know how to look. The night sky that our ancestors knew as a canvas of visible light, stars and planets, and the pale band of the Milky Way stretching overhead. But the universe we have discovered through our telescopes and our theories is far vaster and stranger than anything they could have imagined. For every bright galaxy that catches our eye, there may be others lurking unseen, their dark matter halos tracing the same cosmic web, but their stellar fires never kindled. This hidden universe is not empty or featureless. It has structure and complexity, history and evolution. Dark galaxies are born from primordial density fluctuations, shaped by the physics of cooling and collapse, influenced by their environments and their neighbours. They carry information about the early universe, about the nature of dark matter, about the processes that govern galaxy formation. They are not absences but presences, not voids but structures, not failures but alternative outcomes of the cosmic experiment. The beauty of dark galaxies lies partly in their challenge to our assumptions. We naturally equate galaxies with light, with the brilliant glow of billions of stars. Dark galaxies remind us that this equation is incomplete, that the gravitational structures we call galaxies can exist without the luminous component we usually associate with them. They expand our definition of what a galaxy can be and invite us to think more carefully about the relationship between matter and light. Lessons from the darkness. The study of dark galaxies teaches lessons that extend beyond astronomy. It reminds us that the visible surface of things rarely tells the complete story, that much of importance lies hidden beneath or beyond what we can easily perceive. This is true in science, where the most fundamental constituents of reality, from atoms to dark matter, are invisible to the naked eye. It is true in human affairs, where motivations and meanings often lie beneath the surface of words and actions. And it is true in our own lives, where the most significant aspects of our experience, our thoughts and feelings and relationships, cannot be directly observed by others. The patience required to find dark galaxies is another lesson worth noting. These objects do not announce themselves with fanfare. They must be sought with care and persistence, using specialized techniques and instruments. The astronomers who discovered them spent years developing methods, conducting surveys, and analyzing data before their efforts bore fruit. This patience is a model for any endeavor that seeks to understand something difficult or elusive. The collaboration required for dark galaxy research is also instructive. No single astronomer or institution can tackle this challenge alone. The discoveries we have discussed emerge from teams spanning multiple countries and continents, using facilities distributed around the world and in space. This collaborative spirit, the willingness to share data and ideas and credit, is essential for addressing the most challenging questions in science and beyond. Finally, the humility that dark galaxies inspire is valuable. The universe is under no obligation to make itself easy to understand. It contains phenomena that challenge our intuitions, defy our expectations, and resist our detection methods. Dark galaxies are a reminder that our knowledge is always incomplete, that there is always more to discover, that the cosmos will continue to surprise us no matter how much we learn. The ongoing story. The story of dark galaxies is far from over. New facilities coming online in the next decade will transform our understanding of these objects, revealing populations that are currently beyond our reach and characterizing known objects in unprecedented detail. Theoretical models will continue to improve, incorporating new physics and making more precise predictions. And the interplay between observation and theory will drive progress toward a comprehensive understanding of how dark galaxies form, evolve, and fit into the broader cosmic picture. Future generations of astronomers will look back on our current understanding as primitive, just as we look back on the astronomy of a century ago. They will have tools and techniques we cannot imagine, and they will make discoveries that would astonish us. The dark galaxies we have found are likely just the beginning, the first glimpses of a vast population that pervades the universe. This ongoing nature of scientific discovery is one of its most appealing aspects. There is always more to learn, always another question to ask, always another mystery to explore. The universe is inexhaustible in its complexity and wonder, and the study of dark galaxies is one small part of the endless human quest to understand our cosmic home. A moment of wonder. As you lie here, perhaps on the edge of sleep, take a moment to appreciate the strangeness and beauty of the universe we inhabit. Somewhere out there, beyond the stars you can see, beyond the galaxies that fill our telescope images, there are structures of dark matter spanning hundreds of thousands of light years. These dark galaxies contain the mass of billions of suns, yet they produce almost no light. They have existed for billions of years, evolving slowly in the cosmic darkness, waiting for curious beings on a small planet to develop the technology and the insight to find them. The atoms in your body were forged in the hearts of stars, in galaxies both bright and dim. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were created through nuclear fusion in stellar cores and scattered into space by supernova explosions. You are made of star stuff, connected to the cosmos in the most intimate way possible. And yet most of the matter in the universe is not like the matter in your body. It is dark matter, invisible and intangible, interacting with ordinary matter only through gravity. This dark matter shaped the universe, providing the gravitational scaffolding on which galaxies formed. Without it, the stars that made your atoms could never have existed. You owe your existence in part to a substance you cannot see or touch. Dark galaxies are where this invisible majority of the universe becomes most apparent. They are the places where dark matter exists without the luminous accompaniment we usually expect. They remind us that we live in a universe dominated by darkness, where light is the exception rather than the rule, and the